Good, I found you. Good morning, everyone. Howdy, howdy. My name is Brett Lewis. I'll be the chair today, so if you have any questions, concerns, complaints, come to me. Well, we're going to start this as quickly as possible. I would like to first acknowledge the traditional elders of the lands in which we meet and acknowledge that these were always lands of teaching and learning. But without further ado, I would like to introduce Carly Randall and bring her up to the stage.
All right, wonderful. Well, good morning, everyone. Thank you all so much for coming to the talk this morning. I'm Carly Randall. I come from the Australian Institute of Marine Science, and I'm really excited to be here today to talk to you all about some of the learnings that we've gained over the last 5 years of research in the area of coral seeding. I'd also like to acknowledge the traditional custodians of the lands on which we live and work and pay my respects to elders past, present, and emerging, and also extend that acknowledgement to any First Nations people who are in the room today with us. So as we've seen throughout the week, many of the projects that have been presented at the symposium are really the result of really large partnerships, and ours is no exception. This is the wonderful CAD team. I'm presenting this work today on behalf of all of these fantastic collaborators, so I wanted to acknowledge them here. Considering the RAP program structure, we fall within the Coral Aquaculture and Deployment Subprogram, and our aim is really to undertake the research and development to produce pipelines from the aquaculture facility to deployment of coral seeding devices at scale. And we have a 5-year goal of being able to deploy over 1 million seeding units per year. So our program feeds back into all of the cross-cutting programs of RAP, but in particular the translation to deployment cross-cutting program, as well as the modeling and decision support. So the translation to deployment team, they're really operationalizing coral mass deployments. And then the modeling and decision support teams we're feeding data to them, and they're feeding information back to us in terms of making deployment decisions about where best to deploy and when to deploy. So the approach that we're taking to undertake coral seeding at scale comes from the terrestrial world of reforestation. They use an aerial reforestation method that we're trying to adapt. And the approach looks something like this, where you have a seedling that is established growing on a substrate. That substrate is then inserted into a carrier device that has some protective features that can enhance the survival of that seedling. And then those are released over degraded habitats from the air, or in our case, from vessels at the surface of the ocean. And an important component of this is that the deployment of these devices is really information and technologically driven. So at a really high level, our coral seeding approach begins with a modular production of corals in the aquaculture facility. So we've designed these sheets that you see here at the bottom. They have modular units, and Michaela Nordberg will be talking about all of the aquaculture facility components of this research later today. So I'm just going to kind of skip over that for now. The second step is to then transport those corals to site at very high density transport systems. The idea is then to assemble the seeding devices at the surface on site of deployment. And so the pink sheet there is actually broken up into modular sort of units or tabs. Those tabs are then inserted into a carrier device, and that is then what is deployed from the surface. So what I'd like to do today is talk you through 3 focal areas of research and development that we've done in the CAD sub-program over the last 5 years. So the first of those 3 areas is in the optimization of that seeding device design. So what should that device actually look like? And that's really informing our understanding of the what in terms of coral seeding. The second focal area is all about trying to understand what the environmental drivers of survival and growth are for these corals, and to do this across taxa. And so this is informing our understanding of who, so which species we should be deploying, and where it's best to deploy those. And then the third focal area is intended to allow us to start figuring out how best to upscale this deployment to the millions of corals per year, and that's getting at the how of coral seeding. So I don't have a whole lot of time to give you deep dives into each of these areas, so what I want to do is just highlight a couple of key studies that explain to you all the evolution of the thinking in each of these three areas of R&D. So the first one will be about optimizing that seeding device design. And it's important to say at the start that 5 years ago, we set out a list of key device design requirements. So these were kind of non-negotiable things at the start that we had to, constraints we had to work within. That first one is that the system has to be modular. We had to separate the settlement surface from the deployment device. And the reason for this is because space equals money. In an aquaculture facility, it's very expensive to keep these corals alive. And all the modelers who are working on this were telling us it's simply not feasible if you want to settle on the same devices that you deploy at mass production to do that. It's simply too expensive. And so in the method that we've developed, the corals are maintained at very, very high densities in the facility during transport and prior to assembly. They also need to be conducive with automatic processes. We also needed the devices to be able to lodge into the reef matrix and to minimize their movement. We need to be able to achieve high survival above background rates. And the devices, of course, need to be environmentally acceptable, readily manufacturable, and easily transported. So a couple of the key questions in this space at the beginning were, okay, well, what's the best shape for this coral seeding device? What's the best orientation in which to put the corals in the device? And how can we protect those juvenile corals from the pressures they face once they're seeded on the reef? So I'll talk you through a couple of key studies now that we've done. And the first one is led by Beck Forrester and her team, where she took a very early device design, which you see on the right, and looked at how the shape and size of that device influenced the retention of the device on the reef. So she deployed these devices, divers deployed them in large plots on the reef. They were imaged, and then they were revisited every 3 months, and the movement of every individual device was tracked over a year's deployment. And what Beck's team found was that the overall displacement of devices of all 4 of those designs moved less than 20 centimeters from the point at which they were deployed. And then that movement declined even more after about 6 months when the devices started to become cemented into the reef framework. She also found that the devices with an intermediate number of arms tended to move a bit less, although that wasn't statistically significant with these data. At the same time, Taylor Whitman was leading an experiment that was looking at how we can protect the corals from predation or grazing pressure. And so in this study, she used an older device design that compared corals in a control that didn't have any protection, which you see on the left there, with ones that did have protective features on the right. And what she found was that the exclusion device, the one on the right, increased survival significantly across sort of all life history stages and locations and positions in the device. And in some cases, that was survival that was doubled. She also found that side-facing corals performed better than top-facing corals, and that microfragments performed better than spat, and that was pretty expected. When she looked at this in terms of the actual grazing behavior of the fishes, she found that those exclusion devices really significantly reduced the grazing impacts on the spat. And she has this great photo that shows some of that grazing behavior. And shockingly, I think it was shocking anyway, she had over 90% complete grazing on the devices within 48 hours of deployment. So if we don't protect the recruits, they will not survive these pressures. But you'll also notice in these figures that there was much higher grazing at some sites than others. So it is also site-specific and depends on the communities that are on the site of deployment. Moving south, Kathy Page led a deployment in Whoopabara Sea Country, comparing how well corals in side-facing positions did with corals on the underside of the devices. She did this with 3 different taxa deployed in Whoopabara country over a year and found that the side orientation performed better than the bottom-oriented corals across all taxa. The reason for this was just owing to light limitation. There was just not enough light reaching those corals on the undersides of the device. So fast forward a year, the device designs that you see at the top of this figure were kind of the next generation designs. They incorporated protection around the recruits based on Taylor's work. They also kept corals in vertical positions based on those earlier studies. And so Beck deployed these again looking at retention, and also found these devices really didn't move more than 20 centimeters from the point of deployment. That also declined kind of from 3 months on. But you'll see that there was an uptick between 9 and 12 months here in the device movement, and that was because we had some wet season storms that came through and moved some of those devices up to 6 meters from the place of deployment. But overall, the movement was pretty constrained to about 20 centimeters. Okay, so the evolution of our seeding devices kind of looked like this over the last few years. We have this modular system that has tabs that seems to work pretty well. The design that we're using at the moment is this one here on the right. It is a design that's also linkable so that we can actually make through more complex shapes so that these seeding devices on certain reefs could be linked if we have rubble and we're afraid the devices may fall through the reef framework. And so this is the device that we are moving forward with in terms of our research. Grazing protection is obviously really critical, and vertical orientation seems to be best across all the environments we've tested. All right, moving into the second focal area of R&D. So we'll shift gears now and talk a bit about the drivers of survival and mortality on these coral juveniles. So just wanted to give you a high-level summary first. To date, we have deployed 22 experiments in the CAD program. We've tested this across 13 species. We've tested across life history stages in all 3 regions of the reef. We've tested these devices both fixed and freely deployed, and our average yield, which is the survival at the device level at 1 year of age, is 40%. But obviously that range from 4 to 83% is huge, and it really depends heavily on all these factors: species, environment, the method of deployment. So some of the key questions in this space have been, well, what are the key environmental and biological drivers of seeded coral success, and at what spatial scale is the greatest variance in survival of corals explained? So I'll start first with a study that was led by Saskia Jurians. So this was an experiment where we deployed corals across a latitudinal gradient and a wave energy gradient. We had corals deployed up here at Moore Reef, in the central region at Davies, and in the southern region at Heron Reef. And within each of those reefs, we identified 10 sites that spanned a wave energy gradient. And we did that in collaboration with some modelers at Ames, Mari and Ben. And so we asked, does this survival vary across the wave energy and the latitudinal gradient, and how does it vary amongst taxa? And so the results of this first year's deployment was very taxa specific. And so those relationships depended on what species we were deploying where, and also could be a result of latitudinal differences. Now, in this particular experiment, we couldn't disentangle latitude with taxa because we had to deploy the corals that spawned from that particular reef back to that particular site. And so we're still trying to get at how influential each of those variables might be in driving these responses. We repeated this again in 2022, just at Davies Reef, but with a larger number of taxa and also with spat and microfragments. And we again found that it was quite variable across taxa life history stages. And we also found that water flow doesn't seem to be a very good predictor of survival. So if water flow is not a good predictor, then what is? And the short answer is we're still looking into that. For this particular experiment, we are looking into the benthic community composition and other environmental metrics of the sites, the sedimentation, the temperature, and those things. Now, heading back down south to Whoopabara Sea Country, Kathy Page led a deployment that looked particularly at wanting to know at what spatial scale was the greatest variance in the survival of seeded corals explained, and could we identify any environmental correlates of survival? And so this approach took a really nested and hierarchical design. We deployed these 3 taxa across 3 replicate reefs, and in each reef we had 3 replicate sites. In each site we had 3 replicate transects, and in each transect we had plots nested. And what Kathy found after 1 year of deployment was that the highest variation in survival and growth was explained at the smallest spatial scale, so just 1 to 2 meter differences amongst the plots. That was true for survival and also for growth, and for all 3 taxa. So then we said, well, okay, well, are there any differences at that finest spatial scale in terms of devices that survived and those that did not survive? When we looked at the benthic community around those, though, you see in blue are the devices that survived, and in red are the devices that didn't. The benthic communities are really pretty overlapping. But we deployed at all 3 of our reefs. Where we deployed were similar community composition, similar features, and so we said, okay, well, what if we deploy at more sort of extreme environmental conditions to compare? So in the second year's deployment, we deployed at 3 coral-dominated sites and at 3 sites that were algal-dominated. And we did the same 3 taxa seeded to these sites, and what we found was that there was a lot of variability within groups, more variability within groups than between groups. And yeah, again, the survival varied by taxa. So if you look at Montipora aquatuberculata on the right, you'll see it really didn't matter if it was a coral or an algal-dominated site. It was something that was more specific to the particular site that was determining whether the corals survived. So again, we did this analysis looking at what the community composition was around devices that survived and didn't. There was a bit more separation here, and we saw that there was higher survival in plots that had branching and tabulate acropora present, unsurprisingly, but also where we saw Lobophora. There was lower survival in plots where we had a heavy cover of sargassum, red algae, and Paysonalia. And so what we think is happening here is that the presence of low-lying algae might be more able to allow survival of corals, at least for that first year, than the taller canopy-forming algae, which are probably creating more light limitation for those recruits. But again, if you look at these dimensionless PCA, it's still not explaining a whole lot of the variability. So we said, okay, well, let's hone in even further. We know this fine spatial scales are really important, so what about what's actually growing on the settlement substrate? And so Kathy also looked at this, and what we found was that in the short term and over the course of a year, the coverage of crustose coralline algae on the settlement surfaces really was related to survival. So the higher the CCA, the lower the survival. And I think, you know, that's because this CCA that we're using to induce settlement is also really competitive with the coral juveniles. It also illustrated to us that what communities live in the aquaculture facility on the substrates actually tend to remain in the field for quite a long time. And so what we do in the facility really matters in the long-term performance of those corals once they're seeded onto the reef. All right, so enter Jose Montalvo Prano and Andrew Negri and their team, who are trying to now address this using an antifoulant. So they've been testing this commercial non-biocidal antifoulant that is applied to the seeding devices. In that picture, you'll see the antifoulant coating is just in the center portion of the device, around where the coral recruits are located. It's not on the edges or the arms of the device, because we want that to be cemented into the reef so the devices don't move. So they've been testing this antifoulant, and they have found that the antifoulant in general increases survival by about double. It doubles the survival, and it's most effective in sites where CCA is a really dominant constituent of the benthos. Importantly, after a year's time, that antifoul still works pretty well to keep competition at bay, but there doesn't seem to be any toxicity. Those corals grow very easily over that antifoul coating. They just don't like to settle directly on the antifoul coating. So we're working at figuring out how we can apply this sort of near field to the settlement surface to keep competition at bay. Okay, so to summarize this sort of environmental drivers component of the work, we're really seeing differences at very small spatial scales, and I think that this has significant implications for our deployment decisions for seeding, Because if we need to make sort of in real time decisions about where we're deploying, we need to be doing that at pretty small spatial scales. Most of these experiments, the plots aren't very far from one another, but we're still seeing big differences in survival. So we need our sort of AI-guided decision-making to be done at a sort of 1 square meter or smaller scale. Our trends are also species and life history specific, and competition and grazing are both significant drivers of mortality, but can be effectively managed with the design of the device and with some anti-foul treatments. Okay, moving quickly into this final section, procedures for upscaling our deployment. So I'll just start with a high-level summary. Over the last 5 years, we've really seen an exponential increase in the number of devices we're able to deploy on an annual basis. So this is encouraging. But when we put this in the context of where we hope to be, it's still pretty far down there on the y-axis. Our aim is in 5 years to be able to deploy 1 million corals per year, 1 million seeding devices per year. So key questions in this space have been, can we deploy accurately from vessels? How does our surface deployment affect the survival of the corals? And can we increase our efficiency in assembly and deployment? So this past year was the first opportunity we had to actually test coral seeding from a vessel. We did this for about 1,500 devices at 2 reefs, and we deployed these from the vessel along pre-identified GPS tracks. We tested how well devices can be deployed when they're single and when they're linked together, how well the surface deployments work at 5 meters and at 10 meters, looking at accuracy. We looked at deployment from the vessels at 1 and 3 knots, and also the orientation of the devices when they're released from the surface. How do they land on the benthos, if they're stacked vertically or horizontally? And then, of course, all of these were compared with diver-deployed devices, which is the way we've been seeding to date. All right, I'll give you a quick idea of what this actually looks like. So this was one of the first attempts at seeding from the vessel. The surface deployer was able to deploy devices 1 every 1.2 seconds, and we were aiming for every 1 second, so it was pretty good. And you can see there's a single device there. There have been some linked devices. And so we had divers in the water then monitoring and evaluating how well those devices actually land on the seafloor. And the image on the left shows you the surface deployed devices, which are the white ones, compared with diver deployed devices, which have those black spindles in the center. All right, so what we found in this first trial was that 80% of those linked devices remained linked when they reached the seafloor, which is pretty good, although some room for improvement. We also found that the devices landed less than 1 meter from the transect that was laid out, and that was the case at both 5 and 10 meters depth. So we were really happy with the accuracy we were able to achieve with the deployments. And the accuracy was equivalent when the vessel was going at 1 and at 3 knots. The horizontal and vertical stacks landed similarly in similar densities, although the vertical stacks tended to disperse just a little bit more in space, but less than sort of 1 square meter, which is what we were aiming for. And the team is currently underwater at Davies Reef monitoring for the survival, so we don't have that data to present, but we'll have it in hand pretty soon. So another component of this large field trial this past year was to look at how well we could actually transport these tabs at high density and deploy them and assemble them at the surface and then field deploy them. So we were pretty effective at transporting the devices in these racks that were made, although the interior sheets had a bit of mortality, and I think that's owing to poor circulation within those transport systems. And so there's a lot of room for improvement there, just to make sure that we're housing these in the best conditions to keep them alive over the course of the deployment. We manually cut out 30,000 of these tabs. We have a hand cutter, which you can see in the picture in the center there. And that worked effectively with an assembly team. Thank you. But it was pretty ergonomically uncomfortable, and it was also sort of uncomfortable conditions. And so we did compare this with assembly in the aquaculture facility before transport, and that was more effective at the manual level. But what we're doing now is we have a jig that's currently being made that will allow us to upscale the cutting and assembly of the devices manually. And then further afield, we're working with a robotics team to actually put a robotics assembly of this so it can fully automate the process. Okay, the final thing I want to say about our deployment, so just kind of a shout out to another group within the RRAP program who's developing this deployment guidance system. So it's made up of this unit called Reef Scan, which has real-time substrate detection. It's a camera on the bottom of a pole, essentially. It goes at the front, the transom of the vessel, and then it's in real time detecting what the benthos is and then making decisions about yes, deploy, no, don't deploy, and sending that back to a dispenser. So the Reef Scan is working and it's being trialed now, but the deployment guidance system in its sort of final form is still being worked on, and Ben will be speaking about that more later today. Okay, so just to wrap up, I hope that I've given everybody a sense of all the R&D that we've done within the CAD program over the last 5 years. We've really honed in on these sort of 3 areas, and yeah, we'll continue to work in this space in RRAP version 2 and try to get this working at scale. So thanks so much.
Hello. Yeah. Amazing, Carly. Does anyone have questions?
Carly, in the upscaling, what would be an acceptable level for it to move into pilot deployments? Well, acceptable numbers.
Right, yep. So we have a plan over the next 5 years that starts with 100,000 devices next year and then goes up from there, 200,000, 400, 600,000, and then 1 million in the 5-year mark. So that's what we are aiming for. Not all of those will necessarily be deployed by us as researchers, though. We'll start integrating traditional owner-led deployments and tourism-led deployments in that process. So there's a 5-year plan to roll that out.
Any more questions? Yeah.
Thanks. Hi, Carly. Can you say anything about the attachment of the colonies off the devices onto the substrate? Have some of them been in long enough to sort of look at the time scale of that and the effectiveness of that?
Yeah, that's a great question, John. Thanks. So as I mentioned, we've been testing this with recruits and microfragments. The microfragments, as you might expect, will grow off the devices much faster than the recruits. Within 6 months, the microfragments will grow off the device and onto the reef substrate, and so the cementation of the device by the CCA and the coral kind of happens simultaneously in that case. The recruits take a bit longer to grow off the device, but the tabs are about 11 millimeters by 11 millimeters, so if those recruits settle near the edges of the tabs, they actually don't have to go too far to reach the substrate. So we're seeing some within 1 year start to grow off the device, but it kind of depends on the growth rate of the spat and the site as to how quickly they'll grow off.
Same question, actually.
Thanks, Carly. Can you give us an indication of what a single device costs?
Too much at the moment. I actually don't have those figures at hand, but I would guess that they're a couple dollars a device at the moment. And so this is something that at scale will become cheaper. And so we're working to try and identify manufacturers that can do it more cheaply when we start talking about sort of 500,000 or 1 million devices per year. The goal is to get them all components included, the settlement substrate plus device, to be less than $1 per device.
All right, thank you, Carly. I think that is enough for now. Sorry, we're already behind time quite a bit this morning. So we'll move on. Thank you, Carly. Round of applause, please. Oh, and Peter's already on his way up. He knows, he's on it.
Hi, I'm Peter Harrison from Southern Cross University, and together with Chris Doropoulos from CSIRO, we co-lead the Moving Corals RRAP project. And today, what we want to do is highlight some of the key outcomes from this work on the Great Barrier Reef over the last few years, which focuses on larger scale reef-based slick collection, mass culturing, and deployment of larvae from wild coral spawn slicks for reef restoration. We also would like to begin by acknowledging the traditional owners of the land we're meeting on today and pay our respects to the elders past, present, and emerging. And of course, we extend that through to all the traditional owner groups along the Great Barrier Reef on whose sea country we work.
So why larval seeding? Some work we conducted a few years ago, we highlight how propagals are incredibly effective at large-scale seeding in other systems. That includes some of the largest seeding programs in the world, using mangroves and seagrasses as well. So these programs have both persisted for many years and over very ecologically relevant scales. But how about corals? So we do know from small-scale trials that Peter and Dexter De La Cruz and colleagues have done in the Philippines that corals can be restored to breeding populations on reefs within about 2 to 3 years in the Philippines. And some other work that Peter's led on the southern Great Barrier Reef has shown also to 5 years of breeding populations down there. But what's kind of limiting us is this scale. So these works have been relatively small in the scheme of something like the Great Barrier Reef. Some more recent work is showing getting a little bit bigger than half-hectare scales. So the question that we're kind of addressing in the Moving Corals program over these first 3 years is all about, well, how do we scale up larval-based coral reef restoration for effective long-term ecological benefit?
So the aims of the Moving Corals program is to develop this larger scale production of tens to hundreds of millions and eventually potentially billions of coral larvae with strong environmental tolerance that are derived from the collection of wild coral spawn slicks, which are reared directly on reefs and transferred for settlement onto damaged areas of the reef. So how do we go about doing this? Well, essentially we follow the natural coral reproduction life cycle. And the reef restoration, the larval-based restoration, consists of 5 research phases. The first phase is that we need to locate diverse breeding corals. And after mass bleaching events, the ones that are still surviving have increased heat tolerance. So this becomes our source reef for the coral spawn collection. We then undertake spawn collection in various ways and transfer the spawn across to reef larval pools or onto very large vessel components and tanks. After the larvae are fully developed and desperate to settle, so they are fully competent, we release the larvae onto the reef directly, or we settle them onto devices or tiles, etc., before deploying them onto the reef, and that's the 4th phase. And then, of course, to find out what the outcomes of this process are, we need to undertake some longer-term monitoring. So just to highlight those phases in a little bit more detail, phase 1, we identify the source reefs with healthy breeding corals, and we undertake rapid gravid coral checks to confirm that sufficient corals are present with coloured eggs and are mature. We use the predictions of the major spawning nights to predict when we should be out on the reef to collect the spawn. And more recently, we've been working with the CSIRO modelling team to come up with hydrodynamic models which allow us to accurately predict where the spawn slicks will accumulate around reef systems. And for example, last year when we were working at Lizard Island, the hydrodynamic model predictions, as you can see there in the image where the hotspots are shown in red in terms of the accumulation, likely accumulation of particles in a slick, matched almost exactly where we found the slick around those complex reef systems. The second phase consists of capturing the coral spawn. So predictable coral spawning allows us to access tens to hundreds of millions of spawned eggs. And so in 2022, for example, at Lizard Island, it was a split spawning period, so relatively few of the corals present were gravid, but we still managed to collect more than 30 million eggs very efficiently, which shows that this process can operate effectively even in light spawning conditions. Last year, we had a typical mass spawning with extensive coral spawn slicks and were able to rapidly collect more than 350 million eggs in these mass spawning events, using simple collections in spawn nets and buckets.
Another process that we've been looking at in the program is scaling, other kinds of scaling techniques. So rather than more boats out on the water, maybe bigger boats with less people. And this kind of spun out from some earlier work that we did with oil booms, which they worked pretty well, but they're extremely difficult to operate with out on the water once you capture a slick and you need to maybe move it. I won't give you the whole history of it in essence of time, but we started working with a kind of a modification of a Newton net with bags that would roll out. After a couple of years of trialling that, we figured out that didn't work well. So one of my colleagues, Jeffrey Cullen, kind of came up with this idea, which is to put a kind of big scoop on a small barge, and we can get some rainwater tanks on that and pump the slick from the surface of the water directly into those rainwater tanks. And we know that those diaphragm pumps are really gentle on developing embryos. But in 2022, the operations worked really well, but our actual collection was about 500,000 larvae across a few nights. So it wasn't really good considering how much we can collect in a one scoop on a good night. But I let him try again, and last year in 2023, when we had a really thick slick, he made some modifications and got that kind of scoop net, rather than attached to the vessel, it's floating on the surface, so we could skim right on the surface rather than a lot of the water column. So it helps concentrate that. And he came back after 20 minutes to the mothership and had kind of those 2 rainwater tanks full of about 30 million eggs. So a few years of persistence and failure, but with modifications, kind of helped us get there.
So we're now routinely culturing tens to hundreds of millions of multi-species competent larvae directly on the reefs, in the larval pools and on vessel tanks. And we know that we can scale this through increasing the numbers and sizes of these modular units. We're getting up to 50 to 60% culture efficiency out of these processes, and therefore we can start to optimise the way in which we deploy the numbers of these production units on the reef in future. And there are different scales of the pool net systems which have different capacities for rearing X number of millions of larvae on the reef directly. The fourth phase is about settlement and deployment of the larvae. So after 4 to 6 days, typically we've got a whole lot of desperate larvae waiting for the chance to settle on a reef. And so we can settle those onto hundreds or thousands of devices, similarly to what Carly was talking about in her talk. So we settle them onto devices or tiles before transferring them to the reef. And in 2022, we were working collaboratively with the CAD team at AIMS, CSIM, and we mass settled onto more than 1,000 of those devices. And last year, we did some mass settlement on more than 1,400 of the limestone tiles, and we have an estimated settlement rate for about 1/3 settlers on those. So we know that this process can be scalable.
So moving on to direct release of larvae onto reefs, which is where we think a lot of the scaling potential exists. We've kind of been working to this conceptual model since about 2018, where we use high-resolution hydrodynamic modelling to look for high retention areas, and then using different kind of delivery approaches, we can try and pinpoint those areas to try and get larvae en masse onto the reef at large scales, but so they don't just disperse off from our kind of target areas. Maybe it sounds simple, but this is probably our biggest challenge that we've been working a lot towards over the last few years. So one of the first things that we start to think about is, well, how can we actually identify that the larvae we release are our larvae? And so we came up with an idea of maybe tagging those coral larvae and digging through the literature. Dying larvae kind of, was a potential thing that we thought might be viable. So we ran some early tests on that in 2019, little pilot experiment. It was quite promising. And then we followed up with some experiments to refine the procedure. And it's really effective. And now we've field validated that. And now we routinely use it for many of our trials. That's published, and the procedure is really easy. Anyone can kind of do it. So basically, a quick journey is in 2021, we started to use these high-resolution models. We did a release from the surface, a cloud relief. We did get a signal in our cloud area versus our controlled, but it wasn't really ecologically relevant, nor after about a year once we were monitoring our permanent plots there. 2022, we then used a lot of instrumentation to try and look for these really low current periods, and we also did quite a controlled manipulative experiment on the reef to look for how effective it can be if we really hit those target slack tides, not slack tides, slack current periods. It's not working. We also kind of altered the way that we do our delivery. Rather than a stationary point source, we did kind of curtain approach of release, and we started using rhodamine to visualise the plume. And we effectively kind of covered a broad area of these patch reefs, a bit over a hectare, and we got a bit of a signal. We found our blue larvae, but it wasn't super ecologically relevant yet. A few months ago, we were releasing from the larval pools near these patch reefs and directly from a vessel as well as having, the CADs and the tiles in the other culture pools. We've got different sensors on the reef and in the air and etc. We've got different really high resolution unstructured modelling going. We really understand the tides very well as well. So it's really important to know what's happening with currents in the area. And we get these really 12-hour periods of less than 0.02 metres per second tide. It's very slack. We've got, things in the air looking at rhodamine and sensors. We're getting really high retention, so it's matching the modelling and the instruments. And you can see that we actually this year got, a 2 to 3.5 times signal from our free releases of instantaneous settlement. So this is 2 days after our release compared to our control plot. What you might see on the far right is that compared to when we constrain the larvae under these big nets, there's 60 per tile. So that's an order of a magnitude higher. So, we're getting more than our no larval release control, but compared to constraining it, where it's almost insignificant. However, the team just got back, a few weeks ago, and you can see after 3 months, actually, those sort of densities at that size actually become meaningless because you get extremely high mortality. So, we're going to now move on to monitoring those corals on the benthos, so that's on the reef, using this micro-imaging technique that Marin Guezo developed and published. It's fully accessible as well, open access. And so we're going to monitor those over these, coming year to start seeing whether, we have effect sizes of the juveniles on those plots, because that's what matters, not what's happening on a tile, but what's happening on the reef.
Okay. So, we are now looking at various trade-offs between mass deployment of pre-settled larvae on tiles versus the free releases and working out how to optimise those. So in conclusion, many of the reef trials show larval restoration enhances settlement and recruitment, even on highly degraded reefs. Pilot-scale developments for the future will be focusing on upscaling the production of hundreds of millions of larvae from genetically diverse spawn slicks, mass settlement on devices, and optimised larval release for multi-hectare restoration. And the plan is to overcome the inevitable juvenile coral loss through increasing larval production and settlement, feeding the larvae to increase energy supplies, co-culturing with symbionts, and selective breeding for increased enduring success. What we do know is that enhancing larval supply and recruitment is essential to restore foundation corals and genetically diverse breeding populations. Thank you.
Now, does anyone have any questions? This is an absolute incredible undertaking, gentlemen. Really innovative and impressive. Thank you. So a question from the Slido: how long do the larvae stay died, i.e. how long can you monitor their survivalship compared to natural larvae?
So in a larval form, at least for a week, but then after that we kind of settle them. But following metamorphosis on the reef, in a lab at least 10 days, but from when we revisited things on the reef, less than 2 months. So yeah, it's not a long-term stay, and it's just for a short-term signal.
So I actually just kind of want to add to that. With the dyes that you're using, are they fluorescence-based? And with your micro-imaging techniques, would you be better off potentially using a fluorescence one and seeing if you can get a stronger signal that way and track them maybe even potentially longer?
Yes, I think the Nile blue does have a light spectra. As with the neutral red, we tend to use the Nile blue because it doesn't have any toxicity. With a neutral red, you have to be really careful with it. So there are light spectra that you could use. You would just have to be careful once the zooxanthellae enter, because then they're going to start setting off different light spectra as well. We haven't applied that, but I'd love for somebody else to give that a go, and it should work too. But yeah, you would need different equipment, so yeah, we try to make it very basic. I'm simple.
Any more questions? We have time for one. So another question from the Slido. Since RRAP Moving Corals trials began, you have 2 years of tracking survivorship and seeding recruits around lizard. What is 12-month plus survivorship of these efforts?
So it varies significantly depending upon how many larvae were deployed, how they were deployed, and the reef environment themselves. And in addition, where we've done trials on the cats. So what we do know is that when you settle larvae onto devices before you deploy them on the reef, that the initial settlement rates are much, much higher, and therefore the numbers of recruits produced are higher than that. But for the other components of it, as Carly mentioned in her talk as well, there is great variability depending upon the substrate, the amount of CCA, and the amount of competitive algae in the system. Thank you.
If we can have a round of applause again, please. Thank you, gentlemen. I'd like to introduce the next speaker. Is Ben Moshirian. Perfect. Thank you. Enjoy.
Good morning, everybody. Before I begin, I'd first like to acknowledge the traditional owners, past, present, and emerging, on the lands that we are today, and the sea country that we operate on across the Great Barrier Reef. I'm Dr. Ben Moshirian. My background is not in ecology or coral restoration. It's actually in robotics and collaborative robotics with UAVs, with sort of surface vessels and underwater robots, and how they work in a team, and in addition, how do they work with humans as well. So it's a little bit different. And I also feel, coming to this symposium, that I'm feeling like I'm standing on the shoulders of giants, all of you, and learning so much, because it's like an underwater universe, because you can go so deep, in each of the little different areas, but we can go so broad as well. So today I'm looking at scaling of technology to automate coral deployments for large-scale reef restoration across the Great Barrier Reef. I swiped this slide, and we're sort of looking at RRAP and its process as we grow over the last few years. And the area that we're trying to go towards is looking at hectares now, and then tens of hectares. And in a way, we're setting the scene to look at how we can operationalize our interventions at a bigger scale. Some of the methods that have worked for us until now may not work in the future, And we also need to identify bottlenecks to scale our operations. So for the pilot deployment program, we're first beginning to look at operating in a reef that you're from the surface about 10 meters. So what this does is it broadens the challenge a little bit technologically. In a sense, we need to develop flexible methods that operate for a range of people and technology, and we also need to scale efficiently because if our technology is too expensive, it lowers uptake, and then we can't scale. And we also need to look at different ways that we can collaborate broadly and make it easily accessible for others and everyone to operate with. One example of that is looking at, phones, for example. In 2007, you have the release of the iPhone, a smartphone, and today we're using it in all sorts of ways. I've seen things where you do, people using their iPhones for underwater photogrammetry for their various monitoring as a real-time field tool. And I'm like, wow, what a great way to enable uptake. And, there's so many different tools out there, and we're only beginning to scratch the surface with how we use them. However, there's so much different ways of doing this when it comes for site selection and choosing the right sites. And then that also creates a trade-off with resolution. The higher the resolution we get, if we were to start straight, the more expensive it becomes. So we begin to look at what is almost the Goldilocks approach for which technologies we use where to get to different sites. And likewise, at what scale do we begin to employ different types of technology such as uncrewed surface vessels, or do you augment your crewed vessels to have autopilots as an intermediary as well? And then there's always drones as well, So then that begs the question around scalability. When we want to scale, does it get more expensive? And perhaps initially it might, but that doesn't necessarily mean that it always will be. The other aspect of this is how we scale, and how do we utilize that technology to drive down cost across the supply chain. And where Carly looked at across the supply chain for the CAD devices, there are particular bottlenecks that we're identifying and looking at how do we further automate, or how do you further grow that? Or also, how do we work with our partners across the Great Barrier Reef, whether they're traditional owners, whether they're marine operators, or whether they have aquaculture facilities, that they will in the future, and this year, next year, more or less pick up most of the capacity for us to grow at scale. And then finally, it's how do we do this without sacrificing engagement? Because you could have the best tech in the world, you can do that, but then if you alienate everybody, you're lost, you lose, And so it's that unity and that coherence between the different elements that really will allow us to grow systematically. So with the pilot deployment program, we'll be scaling exponentially. And we're looking at having an average, for the CAD devices, an average of 5 per year. And in addition, for each of these deployments, as we saw with a lot of the work that Beck Forster, the CAD team, are doing, is that we're looking at ways to make these deployments guided. Because what's the point of putting all of that money and investing in this process if we can't actually guide them and then track them and monitor them so that we get effective restoration? So at the beginning of this process, we have site selection. There's an incredible amount of research and modeling going on through the RAP program, where they're looking at the site level and then narrowing that down so that when you're on water, you can maximize your bang for your buck, in a sense, so that you don't have to almost mow the lawn for large areas of the reef. I mean, naturally we're going to have to do that, but you can actually probably save on a lot of cost there as well. And speaking of, that's where the other element of guided deployments comes in. Is one of the things we're looking at is you know, a lot of vessels today, they have, you know, for fishing, I was looking at, you know, BCF the other day, I was like, wow, that's an autopilot, that looks cool. But, you know, this is a bit more sophisticated. We use these in drones, we use these on surface vessels, and the technology to allow this to happen is you can go the open source route, and it's, you know, very cheap, or you can go, you know, you spend lots and lots of dollars on that. And one of the ways that this can be done is by first perhaps a surface vessel mowing, I call it mowing the lawn, but you can see why. You're going in a very guided transect with a GPS position, and then over time, as you're going through that, you know, you can clearly identify at certain depths, you know, is this a good place to drop? Yes, no. It's too deep, I can't quite tell. Maybe then you employ a secondary opportunity. Maybe it's an AUV, a diver, you know, a mix of both to sort of get a more detailed scan on that. The second element of that is to facilitate this with real-time substrate detection, which is a lot of an opportunity for computer vision and AI. So in this method, we'll be starting at the surface with surface-based cameras, such as the Reef Scan Transom, which was explained earlier as it's a high-resolution camera on a pole attached to a boat. However, there are challenges with this. It doesn't matter how good the camera is, turbidity always gets in the way. And the other one is sea state. So on some days it's clear, fantastic. On others, you can barely see the surface. So that changes one of the questions. One of the ways perhaps to mitigate this is by looking at sort of multispectral wavelengths to allow you to perhaps identify what are the better wavelengths that penetrate depth, and can you use that in addition to other models that you have to do sensor fusion to penetrate deeper for our substrate detection. So that sort of brings in the question of, you know, could you use LiDAR? Or could you use a towed vehicle to go deeper, or again, AUVs as well. In addition to driving, you know, going through the technological process, parallel to this, we're looking at doing capacity building exercises and workshops with different groups along the Great Barrier Reef in 3 regions, purely because, you know, you really need to do this. Because if as I said before, you know, the technology needs to work hand in hand with our engagement and our ability to do this consistently, and with that, like, technical knowledge. Finally, I'm gonna just do sort of a conceptual snapshot into what the deployment guidance system could look like in 2025. At the broadest stage, you've got reef site selection, which I touched on earlier. Then we're looking at the real-time detection for dispensing, the actual dispensing itself, and then finally monitoring. Real-time detection, by using a camera at the front of the vessel, you're able to sort of identify within a range where, you know, is good or bad substrate. In addition, where a lot of the work done at EcoWrap, some work that Juan presented on Tuesday, they've designed a heuristics spreadsheet and model that has different characteristics, abiotic and biotic elements to it, that allows you to pinpoint better and better places to deploy devices and different species, etc. And perhaps at the basic level, I've just put up a few on the screen as well. Now we get to dispensing. Dispensing, once the front camera comes, it falls into the water column, and, you know, guided by AI, a lot of the modeling that we've done, we can pinpoint accurately where it, you know, hits on the reef. And, you know, this constant modeling and refinement of this process will allow us to improve in different sea states, in different areas, get more and more accurate as to where we put that. And while we dispense, we geotag. And why do we do that? So that we can have some compliance monitoring, on the sense that, you know, we can always come back to those spots and find where those devices are. Another element to that is through the aquaculture facility, if you're constantly marking, you know, the life story of the coral recruits onto the devices into the water, and in time through that monitoring practice, you can begin to get a picture of the success rate of our pilot deployment program, both on a species level, but then also at scale as well. I drew this slide to sort of look at, you know, perhaps one day, you know, it'll be like we're having tractors on a boat, in a sense, where you have wider swath lengths to do the detection, and then you have more dispensing, like a boom arm at the back, or it could be the side. Just to look at, you know, different optionality and ways that this can be done. Finally, I was sort of, you know, we're doing some initial modeling at the moment around different technologies and when they're feasible in the field based on a cost per coral device. And, you know, initially it'll be, you know, crewed with some autopilot capabilities. Perhaps in the near future we'll begin to use AUVs to do more specific site selection when required. But the big, you know, two that are quite promising are also using UAVs and uncrewed surface vessels as well, as we scale up into the, you know, larger hundreds of thousands and early millions of devices. Thank you.
Thank you, Ben. Great stuff. Do we have any questions for Ben?
Easy.
Hey, you were that thorough. Ben is oh, we do. We have a Slido question. Will robotics or AI also be able to detect unsuccessful devices for potential removal, or are there plans for unsuccessful devices aside from just abandon?
That's a really good question. Possibly. And that's something we'll take note and think about.
Any more questions for Ben? Well, thank you, Ben.
No worries.
A round of applause, please. So I'd like to introduce our next wonderful speaker, Daniel Harrison. No.
Harrison is my supervisor.
Oh, okay.
Yeah.
I was going to say, I've met Daniel before, and yeah, I was like, oh, there's another one. There's so many Harrisons around. So what was your...
Chen.
Chen.
Yes, Chen.
Oh, yeah. Chen is now going to present on behalf of Daniel.
I'm going to explain that later.
Okay, all right. We'll let him explain.
My name's Chen. I'm from SIMS, Sydney Institute of Marine Science, down at Chowder Bay, Mosman in Sydney. So I'm primarily work on the cooling and shading subprogram led by Dr. Daniel Harrison. He's my supervisor. He's going to give a keynote speech at 1 o'clock this afternoon, this room. So if you are interested, come back in this room. As part of my primary work objective, I'm mainly responsible for the engineering upscale of two technologies. First one, marine cloud brightening. Second one, fogging. So basically my task is sort of working as an engineer to be able to fix the problem and to be able to have it tested on the field, operate those machines, get data and come back, process data and reporting. So today I'm going to share some of the results for the most recent campaign in 2023 and also some of the key results. Firstly, I would like to acknowledge the traditional custodian of the beautiful land and water that we carry out our research on. So MCB, marine cloud brightening, probably you've heard of yesterday, my colleague Peter sort of gave a general overview of the MCB, but essentially MCB is the process of creating larger and brighter clouds that could over the ocean to cool the water down and possibly the coral. So my supervisor, Dr. Daniel Harrison, he developed his concept of applying regional MCB over the GBR to reduce coral bleaching during the marine heat wave. So the whole process I'm gonna explain just shortly. Before and after I joined this whole group, there has been tremendous amount of engineering efforts being putting on to really transform this whole MCB concept into a real world physical machine that you can really test on the GBR. So starting from 2015, Dan's group started to develop this concept. Up to 2022, we actually had our very first prototype. We call it V22 Cloud 1, as you can see, 2022. It's equipped with about 100 nozzles. And my work, I started work at SIMS from 2022, basically working on upgrading the V22 Cloud number 2 to number 3 to get it ready for the 2023 field campaign, and also work on upscaling into the 4th generation. All I want to say is there has been incredible amount of iterative engineering efforts has been putting into upgrade those machines, go out to the ocean, spend a good a month or a month and a half to really test those machines to make sure we are delivering this concept into a real world product. So when I first joined SIMS, my main task, as I mentioned earlier, is to upscale the prototype. So I was given a, as you can see, a snowmaking cannon producing billions, a few hundred billions of droplets per second from just a short glass of water. I was given one snowmaking cannon to make those aerosols, but my job was to double the size. And the target is to get from 4.3 up to 8.6. And apart from upscaling, the actual spray cannon, the other thing is to oversee all the problems that we had in the 2022. As you can see here, very clearly, the blue line indicates the water line. So what happens on the boat, we have all our scientific gear on the boat, stored in four of the 20-foot shipping container, which I'm going to talk later. So basically, the whole process is water gets pumped through by a low pressure pump, go through a few stages of water filtration, 50 micron, 10, and 1 micron. The filtered seawater gets pumped by a high pressure pump up to 150 bar, the pressure that you normally operate and the gurney to clean your car, clean your house, clean the pavement. That's the water line. And we've also got 6 dedicated commercial size air compressors, each rated sort of around 200 bar, but we operate at similar water pressure, similar pressure as water, 150 bar, and each of the compressor is able to deliver sort of around 3 cubic meter per minute. And the compressed air goes through serious stages of air and water separator and pipeline filter to make sure the oil content is reduced down below 0.1 ppm. So, and this compressed air and also the high pressurized water gets mixed up, break seawater down to around 40 to 50 nanometer particle size aerosols. And then we use a giant fan at the back to push the aerosol to the low lying cloud. We call it stratocumulus cloud, 500 to 1,000 meter high, trying to brighten the clouds by using those amazing nozzles. So as you can see here, that's one of the sprayer cannon that I was operating for the 2023 fuel campaign. We've got 2 of them. Each of them's got a 5 nozzle, specially engineered nozzle tower. Each of them's got a sort of around 64 nozzles. So altogether, we've got 2 cannons around 640 nozzles altogether. And so, as I mentioned earlier, most of the scientific gear we mobilize in Cairns for this fuel campaign. And the vessel, as you can see from the right top corner, the Bandicoot, that's the main work vessel, the sprayer vessel I was working on for about a month and a half, living on the boat. Ironically, I've been living in Australia for over 14 years. That was the first time I was up on the reef, and it took 45 days. So that was a great experience working with other engineers and also the ship crew. And as you can see on the right-hand side, we've got a diesel genset that was mainly used for power the whole equipment. On the right-hand side, those are the lovely compressors, noisy compressors. We've got 6 of them, and on the left-hand side corner, you've got the support container with all the oil water separator, water pumps, and every single bits and pieces that are putting together make this concept to work. As you can see, we've got 2 cannon over there spraying millions of aerosols trying to brighten clouds to potentially cool the water down. So there was a lot of engineering efforts to bring all these together. The reason why I want to put these slides up is just because I want to emphasize it's such a lot of effort being putting on, like getting people from different multidisciplinary background together working towards a common goal. So as you can probably see here, I'm on a spray vessel. That's the vessel actually creating what we call cloud condensation nuclear, lovely nuclear sort of thing to make the clouds brighter. And we've got a team working downwind on the other vessel, magnetic. So and this vessel is equipped with all different sorts of aerosol sort of equipment to be able to tell whether we are creating the right size particles and also whether we've got enough sufficient amount of aerosol that's going to change the clouds. And also we've got a team working on Heron Island, One Tree Island, to monitor the background, serving as a control. We've got a team working in the air as well. So my supervisor Dan Harrison, he's working in the air. So we're working in the aircraft equipped with more than 20 instruments on the wings, inside of the cabin, to make sure to go through the targeted clouds to be able to tell whether the clouds has been seeded by us or not. Apparently, from the preliminary results, we can say that we've changed the clouds. Next slides. Okay, so for me as an engineer, I'm interested in a lot of engineering parameters in making sure this whole process is safe and less risk to run. So I'm interested in a lot of parameters such as air, water flow, pressures, and also the temperature of the compressors, different sorts of engineering parameters. We monitor them every single second. So at the end of the day, there are a lot of data I have to deal with. And from the results, as you can see here, because I'm running out of time, basically from the 2023 fuel campaign, as you can see here, I've dealt with the 2 sprayers separately because they are essentially 2 different individual systems. As you can see here, for V22-1, one single sprayer, it's got 6 different spraying types. And what I want to highlight here for V22-1 and 2, the spray type number 1, 6, and 1 are the ones we expected. And from all the engineering results, we've done some plotting. So all I want to say here for these slides is for V22.1, it's operating like stably. So 87% of the time is running at what we wanted. For the new upgrades, which we put it on, it's running perfectly. 90% of, almost 90% of the time is running on at what we wanted. And from the downwind vessel magnetic, it's capturing the aerosol sort of dry particle size, sort of around 50 nanometer particle size. That's aligned with what literature has recommended. And and we've doubled the production rate as what I was asked for. That's why I'm still presenting here, I guess. And last slides. Okay, 1 minute. So this is actually very important because what we measured here, the power draw is sort of around 345 kilowatts. For those who are not from engineering background, it's the power sort of around for a sort of like a Mercedes-Benz AMG model, a twin turbo 4.0 engine that can possibly output. That's the energy not needed to drive the whole MCB machine. And apparently those compressors are the main sucker. So they suck sort of around 95% of the energy that used for the whole plant. And last of all, I just want to highlight what we got is extremely higher than what the previous theoretical research being proposed. They were saying only 40 kilowatts is needed, but actually what we got is more than that. So that highlights the importance of getting physical research done on this topic. And in summary, it's a great upgrade. My job's done, and was very first comparison monitoring of the parameters and at scale, and we've got the right size and the right amount of aerosol. And last of all, I would like to thank everyone who worked together on the boat, the ship crew members, and also everyone else involved in this project. Thank you.
Thank you, Cheng.
Thank you.
Hello. Yeah, thank you, Cheng. That was great.
Yeah.
We have 1 minute for a question. Yes.
Thank you very much. It's very fascinating. My question might be outside the scope of your research, but out of interest. Do we have any data on how effective this cloud brightening will be to prevent coral bleaching? Yeah,
I think there are a separate team who are working on the coral side of things. As I said, it's such a large multidisciplinary project. My main area is in engineering. I'm giving a problem, so I'm giving the right particle size, but there are a team working on the cloud physics. There are a team working on the coral health. Yes, definitely. I think we have data for that, but unfortunately, I'm not the right person to ask. Oh. Yeah, you can talk to Peter. Peter's got some. He's working on the coral, so in our team. So yeah. Thanks very much.
All right, I'd like to introduce our next speaker, Aric Bickel, who I had the pleasure of meeting this morning. I'm sure he's going to give a great talk.
Thanks, Brett. Thanks to the organizers for letting an interloper from the States come and present as part of this. So my name is Aric Bickel. I'm SECORE's Director of Technology and Implementation. And today I'm going to be talking about using practitioner networks to develop technology. Oh. There we go. So we were asked to share something personal kind of at the start of this. So I thought I'd share this. I grew up mostly on the interior of the United States, but my grandparents lived on the coast in the southeast portion. I spent a lot of my summers and a lot of my time out there, and that's where I developed this love for the ocean. This is where that passion developed in 12-year-old Aric standing there. And it is that passion that has kind of ended me up working here with SECORE International. And for those who aren't familiar with us, we're a nonprofit organization that's focused on developing technologies and tools and methodologies and training folks on how to use those for the scaling of coral restoration. We're about 16 people. This isn't quite all of us, but it's a good representation of who we are. We're pretty geographically distributed. We have a team in Germany, the United States, and field teams in Curacao and Mexico. And largely our work has centered in the Caribbean, focused on kind of larval propagation, sexual reproduction of corals. However, over the last several years, we've made some inroads to working in the Pacific and in several other places around the world. That includes having the opportunity to come out on several of the GBR expeditions to the with aims to the Great Barrier Reef. This is from 2022 in the expedition out to the Wapabura country. And so lucky enough to do that and to be able to exchange some ideas and work with folks out here. Generally, when we talk about our program, we split ourselves into 3 areas. We have a research team, a technology team, and an implementation team that which is what we call the training and capacity building arm of what we do. And those 3 areas working together is our model for working towards kind of scaled restoration or enhancement. But I think for the purposes of this talk, what I want to do is look at it a little differently, where, you know, from the start of our organization, the ecological research that we've done has led to the technology that we've developed. Those 2 programs working together led to the development of this implementation, this training capacity building program. Through that program, we developed this practitioner network of partners who are utilizing our technologies. But what we didn't quite anticipate was how big of the impact that practitioner network would then have back to those other 2 programs, to the research side of what we do and the technology development side of what we do. So this is what I'm going to spend the majority of our talk, or my talk, talking about from here. And so it's a little more process than results, but I think it's important as a consideration for a model of doing this type of development. So when I talk about our implementation program, SECORE doesn't see ourselves as the appropriate implementers of enhancement or restoration. Rather, we see it as far more appropriate, ethical, and in the end sustainable to identify groups have the ability to put these tools into practice, to provide them with the training and the equipment to do so, and to then hand that program off for a sustainable program going forward. And we developed what we believe to be a pretty comprehensive program for doing that. The 5 years is kind of an estimate depending on where the group is, but that's largely the size and shape of our program. It's a little bit of a deeper look into that, and I'm not going to spend too much time on this slide, but just to say that there are more aspects to it than just the training of how to do the specific work. We spend a fair amount of time on sustainable fundraising, organizational development, things like that, as we build these groups to being able to set this up and carry it out entirely on their own. So that first 3 to 5 years is what we term kind of phase 1, where the focus is on learning, equipping, fundraising, and handing that program off. The hope is that many of these groups will then move into what we're calling a phase 2, where we are providing direction on how them to become the trainers and bringing other groups into this program and to focus on scaling. And that's how we take kind of this nucleus of investment and expand that impact out. This is what the current network of partners in the Caribbean looks like. So we're in 10 different countries here. The blue dots are our staff centers. The orange dots are those current implementation partners, and the green dots are those, we're calling them second generation sites here, but are those expansion sites that we are not the direct relation to. Those are sites that those groups have brought on underneath their umbrella. And so our relationship with them is tangential. And this is where we hope several of those groups kind of move towards. So what do these groups look like? Largely, they are small, 3 to 5 staff. They're almost entirely female run, and they're mostly nonprofits. And there are certainly a lot of diversity kind of within context within these groups and type of groups they are, but they face a lot of the same challenges. So low infrastructure is one of the bigger ones. Very few of them have land-based facilities, and if they do have them, they're at kind of research experimental scale. There's limited capacity to kind of operate large land-based facilities, or there are certainly kind of recruitment limitations there in those places. And increasingly, in the Caribbean context, they're facing limited gamete supply. And that's for a number of reasons, but the stony coral tissue loss disease and the current bleaching is not the least of which, leading to those populations decline and thus limited gamete supply. I want to highlight one group in particular. It's the most mature group in our program. This is Fundamar in the Dominican Republic. They just made that transition from that phase 1 to phase 2. And this is kind of the model of what we hope a number of these groups are going to move towards, as far as kind of building on those initial trials to keep growing. And they are not happy with these numbers. They're still pushing on this, but this is still substantial growth in just an initial 5 years. What's not represented here is the quadrupling of their budget that they saw over this as they successfully fundraised, and also more than the quadrupling of their staff, going from 7 people to, during spawning events with seasonal staff, they have almost 40 now that are working within this group. So this is kind of the model, the big inspiration group, but there are several groups behind them that are kind of following in those footsteps. So when we talk about how, working with these groups has kind of from the bottom up affected the way we look at technology development, it's adjusted our focus to some degree. And we work outside of these 3 areas, but a lot of what we've been focusing on is an entirely in situ process. Where can we move things to not relying on those land-based facilities? Certainly looking at where can we be the most gamete efficient, kind of in the realities of the current situation in the Caribbean. And looking at things that are transferable and adaptable. If we can't quickly and easily train folks on how to use them, they're not nearly as valuable. And if we can't adapt them to the context of those sites, similarly not as valuable. So a couple examples. I think many of you in the room have seen several of these, but we've developed these core rearing in situ basins that allow for the rearing and settlement process to be done entirely in situ. We've been working on developing mass collectors to allow for the utilization of the common nurseries, fragmentation nurseries around the Caribbean for kind of mass collection with relatively low numbers of staff to utilize those nurseries. And we've been working to develop a suite of seeding devices that can be adapted to the site and kind of chosen based on the type of habitat, the type of species folks are working with, the state of those reefs, and the local logistics available. So, the advantages of this for technology development are, because there's this large network, we're able to quickly get things into the hands of some of the practitioners and get that quick feedback and iteration into the program. Quick is in quotation marks because we're still talking about larval corals, so we're talking about, a year plus if we're looking to get survivorship results, but in comparison to what it otherwise would be quick. There is quite a bit of diversity within these groups, so there are a number of perspectives, and a lot of ideas come from that, kind of from the ground up, and this is a way that this could work, and kind of adding to our brainstorming and identifying those needs of what could be useful to practitioners. And we've also kind of created this growing market, and which allows us to have a bit more of a foot in kind of negotiating and buying power as a group. It's a big difference to go from buying 1,000 of something to 100,000 of something, and that gives us a lot more power in that realm. Similarly, there are advantages for the research side. The first of which being that you have an increased number of capable people that are in the water. Those groups are making observations, whether that's spawning observations or observations on kind of region-wide events or activities. And they represent a group that is able to do rapid response type work in the case of an event. And the recent example I want to highlight of that is kind of last year during the 2023 bleaching, and this is a manuscript that we have in review at the moment, so I'm not going to go too much into details, but just as an example. And folks know this, so I'm not going to harp on it too much, and I think many of you have seen these degree heating week maps. Essentially, anything below 4, you wouldn't expect much bleaching. Between 4 and 8, you would start to see some large-scale bleaching and some mortality. Anything above 8, and you would expect mass mortality. This is 2022. This is 2023. And so unprecedented bleaching. Most of the Caribbean saw 16-plus degree heating weeks. And so this is kind of a really large experiment, if you want to look at it like that, of kind of what a large heating event might look like. And in October of last year, we started at some of our research sites and some of our partner sites to observe some resiliency and some differing response between those recruits that came from the assisted recruiting process and the wild populations. And so pretty quickly, within a month, we were able to get 5 different sites looking at 6 different species to go out and look at trying to quantify these observations to see if what the qualifying observations we were seeing were actually there. And again, there's a lot of nuance to this, and there's a lot of context, and I don't want to spend too much time on it. This could be an entire talk unto itself. But we did see a pretty significant difference between those assisted recruits and those comparison populations. And so those are comparison populations between wild adults parental adults where we knew that in some of those locations, and fragments that were outplanted at those same sites. So, the big question here is the mechanism, right? I think we were able to pretty squarely rule out genetic resistance in there. It seems to be size and age related, but the mechanism itself is something that requires further study, and I don't want to go too far into that now, but it is a good example of this network being able to contribute quickly to kind of the research side of things in the face of an event like this. So, looking at conclusions, some unexpected benefits of having this kind of practitioner network, and has significantly changed the way we look at technology development, and it really represents a test bed for kind of optimizing and developing technologies, and it's something we're looking to replicate in other areas, including us coming a little closer to the folks out here. We have some funding from the U.S. government to start setting up the foundations of what would a network like this look like in the Pacific, starting with the U.S. jurisdiction. So we're looking for opportunities to kind of build off this initial investment of some of this training we're doing this year, and hopefully this is something we're able to move to in the near future. Thank you to everyone. Without these folks, none of this would be possible, and if we have time for questions, I'm happy to take any. Thank you.
Thank you, Aric. We do have time for questions. Does anyone have any? Well, we got one.
Hey, Aric, great
Jen.
presentation, thank you. I was interested in your phasing. You talk about building fundraising capacity with local partners, and was just interested to hear your reflections about, I guess, how much SECORE is doing that versus, I guess, in what ways you're supporting local partners to do that, what that looks like and what's worked.
Yeah, so the thing that we found that has been the most successful is that kind of proposal writing, or kind of reaching out to the local governments as a partnership. In most of those cases, SECORE is taking a secondary role in either writing supporting letters or being kind of a minor partner on those. But it's been quite successful for these strong local partners to have this international group with this larger network there to kind of be over the top of that, and it seems to add quite a bit of credibility to those proposals, and have been quite successful. And so a lot of those competitive grants proposals that we've been able to do together with them have been the way that that's gone. Yeah.
Well, any other questions? Thank you, Aric. Amazing work. Incredible stuff. I would like to introduce... Oh, he's already up here? No, you're right. Come. We've got to make up time. I'd like to introduce our next speaker, Kuok Yap.
Hi, morning everyone. Thank you for coming and giving me this opportunity to present to you today. So my name is Kuok, and I'm a PhD student with Professor David Craig at the University of Queensland. So based at the Center for Innovations in Peptide and Protein Science. So in the spirit of introducing a little bit of yourself, I grew up in Penang, Malaysia. And how I ended up in this project was several years ago. I guess my supervisors asked me if I wanted to work on the Great Barrier Reef. I took the word on literally and raised my hand and signed up. Little did I know that the project needed expertise in biochemistry and bioprocessing. So after numerous years now, I still haven't really been out to the reef, but I hope our work in the lab will contribute to the overarching aim of controlling COTS, or more how Dave put it yesterday, was protecting corals in general. So I won't go through the factors involved in COTS outbreak, as it's been reinforced multiple times by all the good speakers we had over the few days. The only thing I would highlight, I guess, is the COTS outbreaks are not isolated to this reef, the Great Barrier Reef, but it's a problem faced across the Indo-Pacific region in general. So current COTS outbreaks, current COTS control relies on surveys as well as divers culling COTS individually one by one. Although efficient, any methods to be able to streamline that would be greatly, I think, appreciated. So when I first started as well, I got shown this picture, and I was asked to estimate how many COTS you think is in this little coral matrix. And I can't remember the number, but the number I put out was way way lower than what it was actually is on just one reef. So I learned from early on that cods are cryptic and they are very difficult to find during the day and they are mainly active at night. To compound to that problem, I guess the Great Barrier Reef covers quite a large area, and so if we can develop tools that can be complementary to the current COTS control program, I guess that would be a big help. So the project aim overall is to develop a rapidly scalable process where we could, have to be based on sustainability as well as looking at being able to fractionate large volumes of water to use as potential attractants. So I guess the first thing is, what are semiochemicals? Semiochemicals essentially are natural chemicals that are released by animals, which will then invoke or elicit a behavioral response from another animal, be it the same or different species. So in terms of COTS, we're interested in COTS-specific chemicals that we could potentially use as attractants. So I guess that's the base of, this study. So we based this off a paper that was published by UQ and Ames several years ago, where they showed that if you put a bunch of COTS in a header tank and you allow them to release that semiochemical, and if you place a native COT at the bottom, what you generally see is this native COTS would actually go and move towards that treatment arm. So proving the fact that if you put COTS together, that they release signals which will attract other COTS. But there was few complexities to these issues because the volume needed that needed to be processed is relatively large. And at a point where we were introduced to the project, some of the chromatography techniques that were used require pre-treatments. So one such example is reverse phase chromatography, where your molecules would have to be acidified prior to fractionation. But acidification itself would cause changes to the biophysical properties of molecules, and in many cases rendering those molecules to lose their function. So what we did was we selected tangential flow filtration, or TFF, as a possible solution. So TFF is a method that can be used, and it's called a soft method where you don't have to pre-treat your samples, and you can use it, your samples as is. So just a bit of introduction about what TFF is. Essentially, TFF it fractionates based on molecular weight, so you can separate different molecules based on the size that they group in. Traditional methods of size fractionation actually will block up your column because they flow in the same direction, whereas tangential flow or cross-flow filtration moves in one direction and allows the smaller molecules to be easily allows the smaller molecules to go through the membranes. Hence, you get separation quite easily without blockage. The other beauty about TFF is that it's very much scalable. So anything you do on a lab scale can be easily scaled up to a commercial level with minimal optimization. The other thing that we were hoping to get is something that's globally acceptable. So TFF is used widely, as shown here, by manufacturing. So if you have your vaccine or antibody production, you use TFF right at the end for buffer exchange and formulation purposes. It's also widely used in the food and beverage industry, so you have food dye extraction or wine clarification. This is also used in waste management. So overall, TFF is widely acceptable globally, and it's easily accessible to, say, if you want to set up a plant somewhere else, and yeah, it's widely available. So how do we apply TFF, I guess, to the COTS? How do we use TFF to fractionate COTS semiochemicals? So we replicated what was done in the paper prior, which in a 40-liter tank, we placed 3 to 4 COTS, depending on the size, and in about 40 liters of water. And we did that for about 20 tanks. So what we'll do is we'll place the COTS in them, in the tanks, allow them to release that chemical, remove the animals, and there we have our COTS conditioned seawater with the chemicals that we are interested in. We next proceed with filtration and then fractionation using TFF. And using a 10 kilodalton membrane as our first cutoff, we then get the larger than 10 and the smaller than 10 kilodalton fractions. And from there, we do another fractionation at 30 kilodalton, and that leaves us with a bunch of fractions. And in this, as shown here in this illustration, we got our molecules separated based on size. So this, we demonstrated that TFF can be used for the fractionation of large bodies of water, especially in COTS semiochemical fractionation. We next wanted to test if these fractions had any use in terms of an attractant for COTS. And using the Y-maze behavioral assay, we showed that in this case, the COTS are attracted to the larger than 30 kilodalton fraction, as shown in this graph here. Next, we looked at a few other things, such as meandering, where we show that if the COTS does not detect an attractant, it will just wander around aimlessly. But the moment you put in a fraction that contains a possible attractant, you see this drop in that meandering, and they become quite focused, and they move right towards that source point. There are other factors that we looked at as well, such as mobility, increase in mobility, and also the positioning of them, the animals, towards the treatment arm. And overall, I guess, this indicates that the larger than 30 kilodalton might contain an attractant or a few of them together. We're not sure at this stage. The next thing we wanted to do is characterize what exactly is in that fraction. So we using proteomic analysis, we looked at what is in this fraction. And we discovered a bunch of proteins, but primarily the majority of it are proteins involved in signaling. And one candidate that sort of stood out to us is this epidiamine-related proteins that have been previously thought to be involved in signaling. As a side thing that we worked on as well is we developed a bioproduction platform that can be used to produce this protein. And for one example is the COTS epidiamine protein we have generated at large scale. So if you ever come to a conclusion that one protein is the attractant, there's a sort of a scale-up platform that's ready to go. We looked at the glycomics, and overall what the glycans tells us that this protein are highly glycosylated. Next, we looked at whether this fraction is actually toxic. It's actually toxic, but based on the brine stream toxicity, we can tell that it's not toxic at all. We then wanted to look at winter versus summer. Overall, what we found was in summer, we have an attractant in the fraction, but in winter, we don't actually see any attraction at all. So indicating that this could be winter versus summer, and summer is probably when we'll get attractants in the water itself. In conclusion, I guess we developed a rapidly scalable, easily adaptable method that can be used for fractionation. And the summer fraction is probably where we want to be looking at moving forward. So I guess I'll leave you with just a possible application. So now going back to that complex matrix, maybe we can target this to a more favorable area and get the COTS out of the matrix for easy, I guess, culling. Yeah. And I'd like to thank my supervisor, David Craig, and Cherie and Richard, who are here today, that we've been involved in the work. Yeah.
Do we have any questions? So this is a question from Slido. Are there plans to synthetically reproduce the semiochemicals?
Maybe not synthetic, but a bioproduction platform. Yeah. So definitely, if we can get or identify a particular compound. Yep.
My voice carries so worried. Do you think that that diamond is working alone? You know, that's your 30 kilodalton fraction.
Yep.
Very often these behaviors are respond to multi-chemicals. I'm just wondering if you could make your attractant even stronger if you knew what the diamond was working together with, because there's usually
you're probably right. We probably think it's a synergistic effect of different molecules. Could be proteins, small molecules. we don't know. But with that epidiamine, we actually did express quite a lot of it, and we did test it by itself in the behavioral assay, but we didn't get any attraction, I guess.
Well, thank you for your talk. That was fantastic, Kuok. So I have the great pleasure of introducing the next speaker, Christine Roper.
All right. Hello, everyone. My name's Christine. I'm a PhD candidate at University of Technology, Sydney, based in the Future Reefs Lab. And today I'm going to be telling you about some work in collaboration with Coral Nurture Program, which you heard a little bit about from Paige yesterday. And it's looking at the use of a high-throughput phenotyping device to guide coral stock selection. Firstly, I would just like to acknowledge and pay my respects to the traditional custodians of the land and sea on which I live and work, particularly the Kuku-Yalanji and Irukandji traditional owners, and I pay my respects to their elders past, present, and emerging. So as I'm sure we're all very aware, being at the conference this week, coral reefs worldwide are facing significant declines, which is prompting a range of active interventions to help combat coral loss and maintain reef function and diversity. Selection of corals with beneficial phenotypes is one potential strategy to increase reef resilience through active interventions. And a phenotype is the observable characteristic of an individual resulting from the interaction of their genotype with the environment. Now, corals with identified advantageous traits such as heat or disease tolerance has the potential to bolster reef resilience through increasing the biomass of strong performers within the population, as well as amplifying the abundance of stress-resilient genes within the gene pool. Now, historically, coral phenotyping has been undertaken through laboratory studies, which makes it quite costly and inaccessible to reef stakeholders who require on-ground or in-water applications. However, over the past few years, we have seen the development of phenotyping devices for in-field assessment of coral phenotypes. An example of this would be the coral bleaching automated stress system, which is also known as CBAS. Recently, our lab group at UTS, at Future Reefs, have developed a high-throughput multi-taxa phenotyping device, which I'm just going to refer to from now on as the MTP device, which allows for rapid in-field assessment of coral phenotypes under multiple stressors. So this includes factors such as temperature, light, and nutrients. Now, similar to other phenotyping devices, the MTP device measures active chlorophyll A fluorescence and uses the response of photosystem 2 as a broader holobiont response to stress. And the reason for this is twofold. So firstly, because the majority of coral metabolic requirements are fulfilled through primary production through their algal symbionts, and secondly, because the coral symbiont breakdown is a sign of metabolic stress that manifests itself in chlorophyll A fluorescent signatures. Now, other phenotyping devices, such as CBAS, have successfully resolved both between and within species differences in coral phenotypes using this technique. Therefore, that's really demonstrating its value for restoration purposes. So we wanted to test the ability of the MTP device to do this, but particularly so in the field where it would be applicable to reef stakeholders. So that brings me to the three objectives of this work. Firstly was to investigate the ability of the MTP device to resolve coral physiological performance across a diversity of sites. Secondly was to examine variations in population thermotolerance thresholds and ranges as a means to potentially identify more tolerant populations or individuals. And a third objective of this study was also to assess how phenotypic diversity and genetic structure align. So for example, do we find sites that have a higher phenotypic diversity also have a greater genetic diversity? And this is important because approaches which select corals based solely on their phenotypic traits have the potential to reduce genetic diversity by selecting a subset of the population. However, we know that genetic diversity is also critical for maintaining reef resilience. Therefore, we wanted to understand the patterns between phenotypic and genetic diversity to understand if this approach of selecting more tolerant individuals could have an impact on the overall genetic diversity of a site. So to do this work, we collected 184 acropora and millipora fragments from 3 reefs and 12 sites across the continental shelf of the Great Barrier Reef, just north of here near Port Douglas. And we selected these sites because their cross-shelf location promotes a diversity of environmental conditions. So firstly, we have Lowell's Reef. It's an inshore reef located about 15 kilometers from the coast, a platform reef which surrounds a sand and a mangrove island. And due to its nearshore location, it's characterized by high summer maximum temperatures and greater temperature variability throughout the year. Now, in addition to this, corals growing within the mangrove lagoon at Lowell's Reef are also subject to more extreme conditions, including a higher temperature, reduced pH, and reduced oxygen. Next, we have Tongue Reef. It's a large mid-shelf reef, which is characterized by high summer maximum temperatures and more moderate temperature fluctuations. And lastly, we have Opal Reef, an offshore reef which is characterized by more stable annual temperatures, most likely due to support from oceanic influence due to its outer shelf location. So fragments were collected from acropora millipora colonies for phenotyping conducted on the vessel using the MTP device, as well as for later genetic analysis. So to tell you a little bit more about the MTP device itself, so it actually combines 3 existing instruments. So it uses a PAM imaging fluorometer capable of measuring chlorophyll A fluorescence, 4 broad spectrum white LED lights, and a thermocycler which provides a temperature gradient. 6 fragments from each coral colony were placed side by side in a custom well plate, which you can see in that top right photo. They were covered with ambient seawater as well as glass to prevent any bubbles from forming, and then that was placed onto the thermocycler, which you can see in the bottom right photo. So once the corals were on the thermocycler, they were subject to a 3-step protocol. So stage 1 consisted of a low light adapted baseline at ambient temperature, which in this case was 29 degrees Celsius for 10 minutes. Stage 2 consisted of a temperature ramping of the temperature gradient, across the 6 wells, with temperatures ranging from 24.5 to 37 degrees Celsius. And this was under that same low light condition. Now, once the corals reached temperature, they were then subject to a 15 stepwise interval of increasing light over a 7.5-minute period. Lastly, stage 3 consisted of a temperature ramp down and a return to that baseline light condition for a recovery period. Chlorophyll A fluorescence was measured during stage 1 and stage 2, as you can see from the T1 and the T2 in this figure, and that was to assess the response of the corals both prior to and during stress. For the genetic analysis, we collected genomic DNA from those same acropora and millipora colonies and sent samples to Diversity Arrays Technology for genome complexity reduction-based sequencing. After a series of quality control and filtering steps, we were left with about 2,000 SNPs, or genetic markers, and these were analyzed via a structure analysis and principal component analysis to allow us to assess and visualize population structure across the 12 groups that I mentioned. All right, so a little bit about what we found. So firstly, to assess the thermotolerance of coral colonies to acute heat stress, we used the ED50 of the relative maximum electron transport rate, which is the RETR max you can see in the y-axis of this figure. Now, ED50 represents the temperature at which each colony reached 50% of its initial RETR max value, and it has been used in a range of studies in the past to characterize the thermal tolerance of coral populations as well as individuals, but particularly in sea bass experiments. So as a hypothetical example, the ED50 of this colony would be 37.3 degrees Celsius. So this is showing you the mean ED50 as well as the variation in ED50 across the 12 habitats for the 3 reefs, Opal, Tongue, and Lowell's reefs. So we found that there was a significant difference in ED50 between the groups, with with Tongue and Opal Reef having the strongest performance. Now, in contrast, we found that Lowell's Reef had a significantly lower ED50, particularly the corals growing on Lowell's Reef Flat, which is that top group there that you can see, as they were actually already showing signs of visual stress when we collected these colonies. In addition to having the lowest ED50, the Lowell's Reef Flat corals also had the greatest variability in performance of about 4 degrees Celsius in ED50 between the poorest and the strongest performer. When we looked at the top 10% of colonies with the strongest performance, or the highest ED50, we found that they were spread amongst habitats and reefs across the continental shelf, as you can see from the red dot in this figure, sorry. So this suggests that individuals with potentially greater thermal tolerance are well distributed throughout the system, irrespective of the environmental conditions. Moving on to the results from the genetic analysis. So this is a figure here showing you a principal component analysis, and it's showing that there's significant clustering amongst the 12 habitats with no discernible population groupings. So this allowed us to infer that all 12 groups belong to a single interconnected population. Now, alongside measures of population structure, we also looked at genetic diversity to assess the richness of the gene pool for each of the subpopulations, and we found that genetic diversity was fairly similar across the 12 groups, with the exception of Lowell's Reef Flat, which had a significantly higher genetic diversity compared to all other groups. So when we think back to that third objective I mentioned, where we wanted to look at how patterns in phenotypic and genetic diversity align, this figure here is showing you the larger the circle, the larger the value for the trait, either ED50 or genetic diversity. So firstly, given that all 12 habitats belong to a single population, we determined that phenotypic diversity was not driven by the underlying genetic structure. Secondly, you can see for the most part that patterns in genetic diversity don't really match patterns in ED50 values. With the exception of Lowell's Reef Flat, the top group there, we did find that it had the highest variability in phenotypic performance and also the greatest genetic diversity, which could indicate that variations in the thermal tolerance of the corals at this site are driven by the greater richness of the gene pool in this subpopulation. So just to finish with the implications of this work, so firstly, we found that the MTP device complements existing phenotypic devices and provides a viable means of resolving differences in phenotypic performance of acropora millipora corals across diverse sites. The presence of naturally stronger colonies scattered throughout the population is an encouraging finding for bolstering population resilience through potentially through strategies of selection and propagation at a local scale. We found that phenotypic diversity did not align with genetic structure, and this suggests that proactive local management aimed at the selection and propagation of more resilient colonies should have little impact on genetic diversity within this region. Finally, the use of the MTP device provides a low-cost strategy for practitioners to select stock, which is immediately implementable and could help enhance reef resilience. And with that, I just wanted to say a big thank you to funders as well as to Wavelength Reef Cruises, who provided a lot of in-kind support for this project. So thank you.
Thank you, Christine. Wonderful work. Do we have any questions for Christine?
Just a quickie, Christine.
Sure.
So if I bought you some coral samples, how long would it take start to finish to get that analysis done on the boat?
Yeah, thanks. I probably should have mentioned that earlier when I say high throughput and rapid, what that really means. So with the MTP device, we can measure about 4 genotypes or 4 colonies of corals in about 40 minutes. Yeah.
Thanks so much, Christine. That was really great. I'm just wondering
but then also, sorry, were you able to hear that?
Yeah, I did.
Okay.
Yeah, thanks.
And then some potentially longer-term heat stress experiments, how those might differ.
Yeah, that's a really good question. So with this study here in particular, we wanted to kind of validate the MTP device within the field, but the device has been developed by somebody else in our lab group who has been doing a lot of sort of comparison and validation studies alongside sea bass in the lab to really get to those questions. And so far, he has found that for the most part, the results are very similar between sea bass and the MTP device. In terms of the sort of longer term heat stress, I would say that there's, I think, always challenges there in sort of looking at chronic versus acute heat stress and whether they line up or not. I think there needs to be some more studies done to really check on that. Yeah.
Thank you, Christine. Round of applause, please. So I'd like to introduce our last speaker before lunch. Yeah, you did it. I've never pronounced your last name before, I just realized. So, Koukoumaftsis? Yeah, pretty good. Loni Koukoumaftsis.
Thank you very much. So before I get started, I'd just like to acknowledge the traditional owners of the AIM site where all this research took place. And I'm going to talk to you about out-of-season spawning and how that can possibly, hopefully, help with reef restoration. So, which button is it? Big one, thanks. Okay, so we should all know that every summer the Great Barrier Reef corals mass spawn, and it's great for reef renewal, but it actually creates a larval supply bottleneck. So we're restricted to those summer months to do any work on larvae. So we've always known that if we could control the reproductive cycle of corals, we could really accelerate that understanding of the early life cycle of corals and advance that work into the biology. So in order to do this, we need to understand, firstly, what governs the reproductive cycle of coral. And this is fairly well known now in the literature, ranging from sea surface temperatures from early late gametogenesis into lunar profiles and photoperiods, down to the actual nights of spawning, particularly the period of darkness post sunset and moonrise. So if we can have advanced control over these environmental variables, then we're one step closer to being able to get corals to spawn on cue. So I'm lucky enough to work at the National Sea Simulator at AIMS, where we have the advanced capabilities to control these environmental parameters from temperature, salinity, CO2, moonlight, and photoperiod. So it's really a marine scientist anachorous playground where you can have such advanced control over these areas. So every year we do mass spawning at the CSIM, where we collect wild gravid corals, bring them into the aquaria tanks, and spawn them on those expected nights after full moon. But we also have a captive ambient breeding program where we keep corals in outdoor aquaria under an ambient temperature profile. This profile is based on the Davies Weather Station 18 years worth of averages, which don't include the most recent bleaching years too. So the advantage is that we're controlling the temperature and we're not exposing these broodstock to those large degree heating weeks, which we've heard about throughout this conference. These are applied daily through a micro-programmable logic controller, so we kind of set and forget, and it allows them to synchronise into that seasonal temperature profile. And regularly these captive coral broodstocks spawn in synchronisation with those wild collected corals. So in terms of developing an offset profile, we simply took this temperature, offset it by 6 months, and so as currently now back at AIMS, these corals are coming into the summer period where we expect some spawning in the next month. Over the last 10 years, this project's been going for a very long time, we started to generate F1 broodstock from those wild collected colonies. From 2014, we started developing F1s across 5 different acro species and 1 Montipora. And once we'd felt we had enough broodstock and they were of expected size or age to be reproductive, we applied that 6-month offset profile in June 2019. fantastic. Within 1 year, we had pigmented eggs in 2 of these colonies, a millipora and a hyacinthus, and that was in the winter in June 2020. Unfortunately, we didn't ever see them spawn, and we think what happened is that we weren't providing offset photoperiod or moonlight, so they didn't have those environmental variables, and it's likely that they spawned unobserved, unfortunately. So we added photoperiod and moonlight in 2020, and then we had even more corals synchronise into this profile. So we had 6 corals developing eggs. So we thought we were on the money this time, but unfortunately, again, we didn't see any spawning. And this time when we looked back at the data, it looked like there was some moonlight corruption in the profile in the month, that critical month leading up into spawning. So we didn't give up because we were really stubborn and we want to make this happen. So we really closely checked our environmental variables and kept going. And in 2022, we finally observed the spawning across some colonies. So we had 8 colonies spawn, producing 15,000 larvae. And not only that, we actually managed to fertilise and settle millipora and LCI. So not only are we producing reliable spawning, we were getting successful recruitment. Those keen-eyed spawners would recognise that May is not actually offset for the mid-shelf expected spawning time, but this year and this data was a split spawning year. So this is why we had spawning across May and June. So June was even more successful, and we had 38 colonies producing 100,000 larvae, making 8 larval cultures across 4 species, and also settling 4 Acropora species and closing the life cycle, producing F2s in captivity. And then in 2023, we had similar results, except we had 1.3 million larvae produced this time, primarily from the 6 Montipora aquatuberculata, which spawned, so creating a lot of opportunities for work on those larvae. We also closed further life cycle of the Montipora and an Austera colony. Again, this May 2023, this time it wasn't a split spawning year, but what it was that it was an inshore full moon, and these broodstock, the Montipora and the Austera, were collected from the Palm Islands, so they were expected to go at this time. And then in June, we also got about 500,000 larvae created from 54 coral colonies. In summary of those 4 spawning events so far, we've had more colonies spawn in 2023 compared to 2022. We think this is because both the colonies are becoming more sexually mature in the system and possibly further synchronising into these offset profiles. So we're getting better as we go along. What's really striking to me is when we analyse the data, the night after full moons are spawning within the predicted times in the literature, and we're using the Baird et al. Spawning database. So even though these corals have never seen the reef, they've never even seen natural sunlight because they've held in captive indoor aquaria, they're still so synchronised into these environmental conditions that we're providing them that they're spawning within that expected range. And the statistics that we've run have shown no significant differences between years and the literature. This is really important if you want to make really good larval cultures with good genetic diversity. You want them all synchronised within similar nights after the full moon. Also, time after sunset, so spawning time was, again, within the expected literature, and stats showed no significant differences. Now, I'll also add that we have this 6-month offset profile, but it's also 5 hours offset. So we have spawning starting from about 4:30 p.m. For all those people that have done really late night spawning, this is actually fantastic because you make your cultures up, you might check your fertilisation, and you leave by 6:30 in time for dinner to get home. It's brilliant. So what do we do with all this is the main question. We have so far supported 12 separate research programs from internal AIM scientists and externals, ranging from CRISPR-Cas9 work to symbiosis work and settlement work. So what's actually happening is that a lot of these groups are honing their experimental methods and testing a range of metrics that they want to prepare for the summer spawning season. So they're sort of better prepared for that natural spawning event. So we are starting to fast track, hopefully, the understanding of the early life cycle of corals. In terms of future directions, it's all well and good to provide a range of gametes and larvae from species, but we want to make sure that they're physiologically comparable to what you would get from the wild. So we've started doing lipid content of broodstock and eggs, photophysiology on the broodstock, sperm motility, egg size, and competent time to competency from the larval cultures. We want to boost larval production of key species. We try to align that with what the RAP key selection species are to get up into those millions and maybe tens of millions of larvae on tap. In order to do this, we're going to collect from the wild. We want them to desync from the ambient profiles and synchronise into our offset profiles. Preliminary work shows if you time it right, you can do that within 9 months for acroporas at least. We want to include the auto-spawning systems, which you guys might have heard about throughout the conference, to maximise the larval culturing methods. And the proof of concept has occurred where we know we can offset 6 months. So theoretically, if you had 12 separate rooms, you could have spawning every month. That's a lot of work for the scientists and technicians who might not be so keen on that, but it is a viable option. A question that might be on your minds in terms of restoration, outplanting, and I want to talk about the scale of this and the limitations, is we know that the pilot scale deployments in 2030, there's 20 species across 3 reefs which are planned. If we do crunch some basic numbers, it looks like we'll need 1 system per species per reef if we want to keep up with that year-round spawning or offer another opportunity to outplant in winter. So it would require quite a lot of infrastructure and staff power to get that as a reality. Genotype requirements is still hotly debated. I just came out of Yui's talk and he talked about having 30 genotypes to be close representation of the wild population genetic diversity. So in terms of having that in a captive system across all those numbers we're talking about, again, it kind of blows out your price, and long-term captive holding would be quite tricky. And lastly, the production cycle keeping up. This would involve deploying recruits as soon as possible after settlement, which is what RAP are doing currently. Obviously, if we're using recruits from this system, we're going to be deploying them in winter, and we don't quite yet have an understanding of what the impacts on acclimation and survival and growth would be of deploying corals from a summer temperature profile into the ambient winter. I'd just like to thank everyone for listening to the talk and acknowledge the entire CSIM team. So it definitely takes contributions from every single team member at CSIM to make this project a reality. And the AIMS communication team and Andrew Negri for his expert spawning advice. Thank you.
Awesome stuff. Do we have any questions for Loni? Plenty of questions for Loni.
Thank you. That's very interesting and exciting. When you're talking about using this broodstock to outplant, do you have a plan for sort of gradually raising the temperature they experience? Because if they're sort of being maintained at these 0-degree heating weeks for spawning, what's your plan for that?
Yeah, that's a fantastic question. There's no current plan, I'll just be clear, to use the larvae for outplanting. It's an opportunity primarily now for method development. Obviously, if there were discussions within AIMS RAP to use this stock, we would definitely want to build in some kind of resilience to the thermal stress that they would experience when they went out there. The last thing you want is you to outplant all these larvae in winter and then a bleaching event comes along and wipes them out. So yes, definitely something that would be involved in the discussions. Thank you.
You mentioned having 12 rooms with 12 different offset corals. Could we have 6 rooms that the corals are capable of spawning twice a year, every 6 months? Can we reduce that time window down?
Yeah, that's another great idea. And I know there's work, Jamie Craig's in particular, who has coral colonies that are spawning twice a year. That would involve, we would just take our offset profile and condense it to 6 months. But currently I'd like to do some prep work in the broodstock, so part of the gamete physiology, and make sure that the broodstock are in best health before we kind of push them to spawn every 6 months. So I would prefer to add an extra room, although it would be more costly. So yeah, definitely we've had this discussion and had to think about trying to push our corals as far. Yeah, good idea.
Hey, Loni.
Hey.
My head hurts a little bit. It often does. So you've changed the temperature and now the temperature cycle, which has put these corals in line with Ningaloo's spawning times. Can you explain, do you know what's going on with Ningaloo, how they're spawning on the dropping temperature and GBR's spawning on the rising temperature?
Yes, I'm not going to be able to answer that question, unfortunately, sorry, because I'm specialising in the Great Barrier Reef captive coral synchronisation. So, sorry, maybe there's someone else out there that can help him with that question.
Thank you, Loni. Everyone give Loni a round of applause. Great talk. So, just before you all duck off to lunch, we're going to wrap everything up. We're going to have a short lunch today because we are behind, but we'll reconvene for the next session at 1:15. Have fun.
talk. Thanks for coming.
Good afternoon, everyone. Oh, apologies for that. A bit of the paella is still stuck in my throat. My name is Brett Lewis. I'll be chairing this session. Do we have all our speakers here? Hands up, anyone? Yep. Okay. Just one sec, actually. Daniel? Oh, it's a video. Oh, I had no idea. Okay, great. Brilliant, thank you. So Daniel Harrison will be giving our first talk via video.
Hello everyone and welcome to my talk. Thanks for coming. As you can see from the bottom of the screen here, I'll be presenting the work on behalf of a very large number of people that form part of the Reef Restoration and Adaptation Program Cooling and Shading Sub-Program. My name's Dr. Daniel Harrison and I'm from the Reefs and Oceans Research Cluster at Southern Cross University. So first, our motivation. This won't come as a surprise to anyone here at this conference, but the Great Barrier Reef is in trouble. And here it's just maybe a new way of looking at it for some of the audience, but I've simply plotted a linear trend line to the average global temperature anomaly since the Industrial Revolution. And I've also marked on there the recent contemporary mass bleaching events recorded on the Great Barrier Reef. As we can see quite clearly, we've passed a tipping point on the Great Barrier Reef where it's now possible for the reef to bleach in any hot summer. And we're seeing that more and more, and typically in most of these bleaching events occur during El Nino years when you can see the spikes on the graph here might be 0.2 degrees or so above the average global temperature. And we're increasing the temperature at a rate of about 0.2 degrees every 10 years or so. So the situation that we have now, a strong El Nino year, in 10 years' time, that'll be an average year, and a strong El Nino in 10 years' time will be another 0.2 degrees or so above that in a global average sense. I've marked on there as well, of course, the more optimistic Paris target range, which we no longer think we're very likely to be able to stick to. And after that, the temperatures are really starting to look quite incompatible with the future health of the Great Barrier Reef. And so the cooling and shading sub-program is about looking into whether there are any engineering interventions that are applicable at scale by which we can help to mitigate bleaching damage to the corals by either cooling the water down or shading the corals so that they have less light stress and less bleaching even in the presence of warmer water. So we can look at the scale of these different ideas, and the direct cooling ideas tend to be fairly limited to small scales, maybe a colony or up to a snorkeling area. Some of the ocean albedo modification type ideas are probably applicable mostly over a snorkeling area, but maybe could be pushed up to the size of an individual reef. And then some of the atmospheric interventions might be applicable over a larger scale, such as the oil fogging or the seawater fogging, or the marine cloud brightening, which is applicable over regional scales only. And the reason that seawater fogging and cloud brightening are green in this figure is because they're the two interventions that we've been actively progressing in the Reef Restoration and Adaptation Program during this first phase of research. So what exactly is fogging? So the idea is to create a low-hanging sea fog just generated from seawater that would float low over the surface of the ocean, be dense enough to reflect a meaningful amount of light, obviously, and to be able to be dispersed over a large enough area to make it worthwhile. Generally speaking, we expect most of the benefit of fogging to come from shading. So even though the corals are heat stressed, by reducing the light stress, it's based on the hypothesis that the corals will be able to tolerate increased seawater temperatures up to a point, if the light is reduced, and there's quite a lot of evidence that this works. The corals experience most of the stress. Everything sort of goes wrong for them at once. There's less cloud cover, so more light coming through. There's less wind stress on the ocean, so there are less waves and less reduction of the light on the sea surface. Suspended sediment settles out of the water column, of course, and so there's also greater water column clarity and therefore more light making it down to the corals. And we've done some research that shows that these periods of doldrums are when the water really heats up and a lot of the degree heating stress starts to build up as well. The question obviously is that going to be enough to then infer a greater survivability to the coral over a bleaching event? And how would you actually do this? So the idea is fairly simple. You take seawater, you use large pumps, and you put it through nozzles that atomize the seawater, much like a sort of a misting machine that you might find at an outdoor concert or some outdoor venues. Although the difference is in those cases, if you're doing it with fresh water, the fresh water evaporates and you just get that evaporative cooling of the air mass. With seawater fogging, a lot of the water still evaporates, but the sea salt crystals are left behind. And if you target those at the right size for scattering light, then you can continue to shade for much longer than if you tried to produce a fog of fresh water. And so we've been working quite hard in the sub-program trying to answer that first question about how much shading is required. And this has been limited so far to tank experiments, both with under natural lighting and also artificial lighting. And just to summarize where we're up to at this point is that there's been a bit of research now and seems to suggest that 15 to 30% is sufficient to impart a bleaching benefit of up to about 3 to 6 degree heating weeks, or that, I should say, the benefit is still there at 6 degree heating weeks. It's not completely overwhelmed. The big question that we're interested in is really whether over a whole bleaching event extending over a summer, if we're just shading at a location during the doldrum periods when conditions are suitable for fogging, is that enough to impart a benefit when you look at the whole summer in aggregate? And the answer to that seems to be yes, although we have some doubts about how transferable some of these results in tank experiments are to the real world. And so the next step's going to be to try this in the real world. And so we've, in parallel to the tank experiments I've been describing, we've been developing a proof of concept system to allow us to get out in the field and just to look at whether you can even really generate a seawater fog, what sort of size droplets can we produce, how much shading does that impart. And the results so far are fairly encouraging. We can make quite a large sea fog, which you can see there during a trial last year over the Great Barrier Reef. And that fog that you can see there, the average shade from boats doing transects back and forth under that fog was around 10 to 20%, a maximum of up to about 27%. Now, I'm not going to present too much more on the results of fogging because they're covered in a couple of other talks coming up this afternoon. So make sure that you see Joe Alro's talk if you're interested in fogging. He's going to go through the entire fogging project from start to finish. Our droplet size is far from what we believe to be optimal. So we think that there's still a lot of scope to tune the technology to achieve quite a lot more shading and hopefully over an even larger area. We estimate that it's probably practical to go out and fog now with a couple of barges, a similar size system to what we tested there, but split amongst more sources, probably up to order of 10 hectares or so. So the next intervention that we've been looking heavily at, and I'm sure you've heard of, is marine cloud brightening. And so the fundamental idea here is that every droplet in a cloud, it needs a nucleus to condense around. Over the ocean, when the air is very clean and free from anthropogenic sources of nuclei and free of anthropogenic, well, not just anthropogenic, but also natural sources of nuclei like dust. Essentially, a nuclei can be just about any aerosol, which is just a small particle floating in the atmosphere. That's all that word means. Over the ocean, most of the cloud condensation nuclei are made up of either sea salt or sulfate-based compounds that have undergone chemical transformations for example, the release of DMS by phytoplankton or even corals themselves. So over the ocean, if we're away from the land, we have typically very low concentrations of these cloud condensation nuclei, mostly either sea salt formed from breaking waves. But the important point is that over the ocean, there can be very, very low numbers of these. And since every droplet in a cloud needs a nucleus to condense around, we get clouds that have the same amount of liquid water, because the amount of water vapor is set by larger meteorological processes. But that amount of water vapor is forced to condense on fewer particles. And so those two glass jars there, they both contain perfectly clear glass spheres, but because the one on the right, the size is closer to the optimal scattering, the optimal Mie scattering size of light, it reflects more light back and appears whiter. Basically, we're looking at artificially enhancing that natural generation of sea salt aerosols over the ocean by taking seawater, much like in fogging, but atomizing it to a size of droplet that's about 100 times smaller and much, much larger quantities, orders of magnitude higher quantities than we're fogging. And when those droplets evaporate, the nano-sized salt crystals left behind form cloud condensation nuclei. And so essentially for cloud brightening to work, to be effective, we sort of need two things. We need the background number of cloud condensation nuclei to be quite low, and we need suitable cloud formations to influence. And so that's what we're looking into over the reef. So I said that was the simple explanation. I don't want to spend too much time on this, but cloud microphysics is immensely complicated. And when we're adding these additional sea salt aerosols, there's a whole chain of processes that could be impacted. And so one of the ways we can look into some of these questions is through cloud microphysics modeling. And we're doing this across quite a range of scales in the sub-program. So again, to start in the bottom right, you can see there the modeling at the scale of an individual experiment where the ship is releasing a plume and we're looking down on it there. So looking at the spread, and the panel to the right here is showing that sea salt aerosol plume released from a ship, and the blue is the clouds. And so it's looking at where the plume interacts with the clouds to brighten the clouds. And that's at the scale of an individual experiment. If we look over at the right, this is looking more broadly at a region over the Great Barrier Reef and trying to test the sensitivity. Are the clouds over the reef sensitive to cloud brightening? And the answer is yes, quite sensitive in this model. And one thing that's interesting to point out is because this shows really quite clearly that we're not making clouds when we look at this cloud brightening technology. We are brightening the existing clouds, and you can see in the cloud albedo here that the change for an individual cloud is fairly subtle. It's filled in a bit more and has a high average brightness. And then, of course, the scales also extend through to looking at the larger Australian region there, and that model scenario there is looking into risk. And so this is looking at a cloud brightening scenario over the Great Barrier Reef and looking at whether it was likely to change precipitation over the Australian region. And the answer, at least in that scenario, was not really. Here, we ran a set of scenarios through the E-Reef's hydrodynamic biogeochemical model. And I just want to really point out two things. I'm only showing one scenario here where we assumed that we brightened the whole reef out to the edge of the continental shelf. And you can see that the cooling is really quite limited to the region over which you're conducting the cloud brightening. And this is a bit of an unusual case, and this is also the reason that this idea could actually work for the Great Barrier Reef, is that we have a large shallow lagoon. And we can see that here if we look at the baseline and the cloud brightening scenario here. I apologize, I've just realized they're labeled backwards, but the blue is actually the cloud brightening scenario and the red the baseline. But the water is essentially captive for a period of time, the residence time within that shallow lagoon, and just like a shallow lens of water on a beach on a hot summer's day, it heats up quite quickly during these events that cause the coral bleaching, especially when we have low cloud cover. And when we run the model and we increase the brightness of the clouds, you can see here that the residence time is reflected. So it takes around 2 weeks or so in this particular scenario for the temperature with and without the cloud brightening to diverge. But then after that point, there's sort of a balance reached between new water coming into the lagoon and cooled water, if you like, or water that was prevented from heating up, flowing back out of the lagoon. And another thing that we found with this modeling is that you can fairly reliably predict if you have a given amount of average reduction in solar radiation, the amount of cooling that you'll get. And we ran here scenarios with both assuming that the low clouds that were actually present in these hindcast scenarios were brightened, but also looking at an equivalent amount of forcing just applied evenly everywhere over the scenario area. And you can see here that the difference between those scenarios is the circles and the squares. And you can see that they all lay on the same line essentially. And so that's quite interesting. And that means that the movement of the clouds over the length of the scenario, which is a couple of months long, and the circulation of the water even out any irregularity in the actual exact location of the forcing, at least on this scale. And then on the right here, because air reefs has a biogeochemical component, we can actually model the combined reduction of stress from light and temperature in the corals. And we're updating this modeling at the moment, but we previously did this work. We did it over those 2 initial bleaching events in 15-16 and 16-17. And what we found was that in 15-16, which was a strong El Nino year with less cloud cover, there was still a benefit from cloud brightening, and bleaching stress was reduced about 50%, but not as much as the following year, which wasn't a strong El Nino, and the cloud cover was higher, where it was about 65% or so. So some colleagues at CSIRO then took some of these results and put them into models that play the ecological models, CocoNet in this case, that predicts ahead over time the coral cover on the Great Barrier Reef based on an ecological model. And so again, these are scenarios that assume that the cloud brightening was effective. They assume that you were able to actually brighten the clouds. And what we found was that consistent with our understanding of how things work, there's only a certain amount that you can brighten the cloud. So you can't just keep doing more and more cloud brightening and getting more and more reduction in temperature. If you had some of these effective cloud brightening scenarios operating over the whole reef during the bleaching years when you needed them, and you also had really strong action on climate change, the so-called RCP 2.6 scenario, then the sort of baseline predicted trajectory in this work that's quite dated now is the dashed line here, and the solid line is with cloud brightening. And so you're able to avoid some of the degradation of the reef by applying the cloud brightening intervention on a very large scale, of course. However, what we also found was that under a more business as usual type climate pathway, you still get that benefit, of course, but that gap that you can exploit in the clouds, it eventually becomes overwhelmed by climate change, and you just can't keep up. There's no more gap to exploit. And so this is very, very strong evidence that, or a strong reminder, if you like, that these interventions, they're really only going to be effective if they're combined with very strong action on climate change. They're no silver bullet on their own. But when we put all of this modeling together, what we end up with is a sort of number of about 10 to 20 watts per meter squared average reduction over a bleaching summer, and that appears to be enough to alter the trajectory of the Great Barrier Reef going into the future. So that then, of course, raises the question of whether we can get 10 to 20 watts. And so that's where most of our research is focused now. And so this is looking at a typical field experiment we've built up over the last few years. from initially testing the equipment that we use to generate the sea salt aerosol spray to atomize the seawater, then looking at the dispersion of that with drones, then introducing an aircraft, and now we're at the point of starting to look at how those sea salt crystals that we're generating are actually interacting with the cloud microphysics. And there was a whole heap of engineering that had to go into this to getting to this point, obviously. And I'd like to point you towards Cheng's presentation later this afternoon, where he's going to go right through the engineering from the very, very early days to where we're at now for the cloud brightening technology. The other challenge that we came up against was that there was no cloud microphysics research capability in terms of an airborne platform in Australia. And it was going to take too long and be too uncertain to try and get one in from overseas, as well as expensive. And so we actually ended up starting from scratch and developing our own. And that's been quite exciting. And Peter Butcherine is going to give a talk this afternoon about some of the exciting remote sensing capabilities. He's not going to go too much into the cloud microphysics for this particular conference, but he is going to talk a lot about the bathymetric LiDAR and the hyperspectral imager that we've been using in our research in this sub-program. And just to give you an idea of what this actually looks like, I've chosen a video here from a not particularly cloudy day, but that's so that you can nice and clearly see the vessel and the plume here without it being hidden by a whole heap of clouds. But you can see us flying up on the sea salt plume here, right where it's going into a very small cloud. And most of the instruments on the aircraft there are designed to sample optically as you go through, and they're measuring the size, distribution and concentration of those sea salt crystals that we've produced, as well as the size, distribution and concentration, of course, of the cloud droplets. So one of the questions that we had to look at in this research, there was some literature out there suggesting that as the seawater evaporated to leave these sea salt crystals that we want behind, that would cool the air mass, much like the misting at the pub, and that would prevent mixing of the sea salt aerosol plume up to cloud. So we've quite thoroughly dispelled those concerns now. So the bottom plot here is upward pointing LiDAR. And so you can see the cloud layer there. Sorry, the bottom axis is time, the y-axis is height. And you can see the cloud layer, the dark red layer there, and you can quite clearly see our sea salt crystals lifting up to cloud base there. And I should mention, by the way, both in the LiDAR data and also in that visual imagery that I just showed you, you can only sort of pick up less than 1% because the sea salt crystals are nano-sized. It's the very few larger ones that are actually larger than what we want that you can actually see optically. So although even that plume coming out the back of the vessel might look quite impressive, 99% of it's invisible. But not to our instruments on the aircraft, of course. And here at the top, these are plan views, so like a map view of the sampling just below cloud base. And these are just illustrating that they're getting quite high concentrations of these sea salt up to cloud. And so that sort of box was ticked. This is very hot off the press. So in the top right panel here, the red clouds are seeded with our sea salt aerosols from the vessel, these cloud droplet radius again, and the blue are the clouds that were right nearby but outside the influence of the plume. And in this case, we saw about a 2 micron decrease in cloud drop effective radius. So about half of what we saw during that natural experiment, but that natural experiment was a very, very large event. Nevertheless, it shows that there's possibly still room to optimize the technology to get even more brightening of clouds. And the panel on the left here just shows the full size distribution as opposed to sort of the mean effective radius. And you can see here quite clearly the difference between the seeded and unseeded clouds. That you've got the similar amount of water inside the cloud, which is the integrated area under the curve, but there's a crossover point. We've shifted the size distribution from larger to smaller. which is consistent with what we expect in that first Toomey effect, that immediate brightening effect of the cloud, which is what you saw in those satellite images. We can also see this and measure it by satellite, by the way, but I fear I didn't have enough time, so I haven't included it here. This research is being done with a very, I guess I'd like to say best practice or better than best practice level of governance and engagement. We have a board and steering committee, independent risk review group. All of the work's done within the Great Barrier Reef Marine Park, which is federally managed, and all the permitting processes for that mean that we have to have community engagement and community consultation, as well as traditional owner consultation. But we go beyond that in all of our RAP, and we actually seek free, prior and informed consent from traditional owners of the Great Barrier Reef before we do any research in their sea country. We're also participating in community panels, and there's a great talk will be given by Samantha about that at this conference. So in conclusion, with further technology refinement, fogging appears to be feasible over areas of up to 10 hectares or a couple of maybe 20 hectares. The next steps for fogging are a longer running experiment. In the initial phase of our app, fogging was really very much proof of concept. Is this even feasible at all? I think we've shown that it is, but it's applicable to two fairly small areas, unlike the cloud brightening, because you need to pump and atomize so much more water. For the cloud brightening, we're fairly confident. I think now that the target is around 10 to 20 watts per meter squared of average solar radiation reduction over a bleaching event. We've shown pretty convincingly, I think, that the dominant summertime clouds over the reef are susceptible to cloud brightening, but we still really need to get a handle on how different states of the atmosphere, different types of clouds, different background concentrations of cloud condensation nuclei, how they affect the amount of perturbation that we get in the cloud. And we've developed the technical capability now to do those experiments. We've just completed a much larger set of experiments this year, which will give us some insight to those questions, but we don't yet have the results fully available. And finally, and very importantly, that emissions reductions are an absolute prerequisite for preserving the reef. It's not an either or, it's an absolutely, we need every tool at our disposal kind of situation, in my opinion. And so finally, I'd like to thank all of the members of the sub-program, as well as the wider RAP team that have just been working so hard on looking into these interventions for the Great Barrier Reef over the last few years. Thank you.
So thank you, Daniel. Now, we don't have a representative to answer any questions, so if you do have some, please, you can email Daniel and contact him outside of the room, sorry to say. But we do have a great next talk coming up. That will be from Manuel Gonzalez Rivero.
Thank you very much. Hi, everyone. Thanks for sticking to the talk in the afternoon of the last day. I'm giving this talk on behalf of quite a lot of people that I would like to acknowledge as well. And I would like to start first acknowledging the traditional owners where we meet, but also the work that in all the countries where we work and live and recreate. And that's across the entire Great Barrier Reef. And I would like to pay my respects to elders past, present, and emerging. This work is work that we've been doing for over 4 years now, and it's recognizing that, in a way, there are various different challenges for us to manage coral reef, and we'll see it throughout this symposium, and the challenges are increasing and increasing. But one of the biggest challenges I see is information. And how do we sort of like catalyze the production of knowledge to a way that informs actions in a quicker way, so we can decide what are our best practices to improve the state of the reef. So we can manage what we then measured. Our information is not always accessible everywhere. We tend to have information that is quite siloed or in different formats. But also, all these two combined means that the advice that we can provide to those that make decisions are coming often like later than they should be. And because the challenges are only increasing over time, it becomes more of a problem to make decisions in a quick but also informed way. And behind the scenes of all this, there's actually various different reasons why monitoring in a way that produces a lot of this information is challenging in terms of delivering the science and knowledge that we need to have. And part of that is that because this is expensive, but also because the way how we collect data can be incompatible in different ways, or we have the access to that information or data sets are limited or perhaps are restricted, and so on. But I think those things are changing in a way, and we are moving more and more into a space where we can collaborate and share more information. Now, the next part of that is that we need to be able to analyze the data. Even if we have the willingness to share that information, we need to analyze it and summarize it. And so that's, in a way, the rationale that sort of kept us up at night for creating Reef Cloud is that there's an immediate need to move faster, but how can we do it in a way that is scientifically robust and help us move the community all along together? So Reef Cloud is an online platform, and it's been growing substantially to trying to actually bring together various pieces of technology or innovations to actually help us fast track or analyze and summarize the state of the reef a lot faster. So then hopefully that information can actually move from being data sets to information to knowledge and then to wisdom to make decisions. So there's three areas that I want to talk to you about it. Reef Cloud offers various different options for bringing best practices in data management so your data is secure and organized so it can be analyzed. It brings machine learning, like particularly artificial intelligence, for extracting information out of images. But also, to me, the most important part is then it allows to bring together various different data sets from various different organizations for different purposes to try to summarize the state and status and trends of the coral reef at different geographic scales. And it uses images because we are now moving more and more in the space of digital data sets. We sort of been collecting images for many years as scientists because it's a lot easier when we are on the water. But images contain a lot of information, but it takes us ages to go through that and analyze it. So then we thought that sort of images as a currency for monitoring, because they provide a lot of capacities for doing quality control and assurance of the data. We can standardize the taxonomy, but also serve as a bit of a tool for guaranteeing the integrity of data collection. So we use the AI models to be able to help fast-track in the extracting of information. So in a way, what Reef Cloud offers to that challenge is to help in bringing a little bit more of that scalable aspect of monitoring. That is not only just about specific people with high-level training and expertise to do it, so it means that it's more inclusive in a way. It allows the data analysis to be 700 times faster, so it's a lot more efficient in terms of extracting data. But it allows also to serve as a tool for democratizing knowledge and sharing information. So hopefully we can actually improve the way how we deliver our knowledge to those that make decisions. I don't have a lot of time to walk you through the entire platform, but if you go to reefcloud.ai, you have really amazing sort of, it's a very intuitive way to get through, but just as a bit of a show here, I'm showing you our data sets from the AIMS long-term monitoring program in Reef Cloud, and it gives you access to ways to organize your sites, your surveys, your taxonomy, share that information with different users, and then also using the CPC style of analysis to classify and extract information from the images that is training a machine behind the scenes to work on that. But I just want to show you how it works or the validations that we've been doing out of the machine learning. And these are 3 different cases that we've been picked from different regions around the world. The first one is the comparison between the estimated values of coral cover and the observed values of coral cover by humans and machine. So the red line is the identity line, so everything is exactly the same, and the dot points are the observations. So you can see that it's quite consistent, and this is work that we've been doing with the Palau International Coral Reef Center over many years, so it's not just a single year of data collection. The other one is about sort of bleaching, some work that we did in Hawaii, where we did sort of before and after, during and after a bleaching event. So what you see there is the temporal series and the x-axis, and the proportion of coral cover whether bleached or not in the y-axis. And sort of you can see that the comparison in blue and red between the machine and the human is quite consistent. And this is about bleached coral, not just coral cover. Shows you that like how the progression of bleaching changes over time, and the machine managed to pick that up. And lastly, this is an example from the right, bottom right, in terms of the precision over time, where we show that with our long-term monitoring program in Australia, how the estimation of coral cover over time is followed by the machine. So the gray area is the estimation by the human, and the red lines are the estimations by the machine. The aspects that I think that are important out of this technology is, as I say, it makes the access to technology a lot more readily available for others, and not only just for us as scientists, but for many other organizations and participants that want to actually be involved in the collection, but also understanding of the state of the reef. So the work that we've been doing actually expands beyond regular scientific monitoring and cover first scientists of Australia, the Indigenous nations, but also community groups. And we've been working quite heavily with the tourism industry here in the Pacific to actually bring together a pool of people that are very interested in contributing to monitoring and using Reef Cloud to facilitate that extraction of information. And one of the, as I say, one of the parts that to me are the most exciting is the reporting back. So bringing that information together and summarizing what's the state of the reef at various different scales. So Reef Cloud uses a range of different models that trying to actually recognize the different spatial scales, different methods, different strategies for collecting data, and trying to bring that together to summarize and propagate the uncertainty from the machine learning and from the spatial analysis to summarize with confidence the state of the reef over time and space. And so that it produces a series of graphs and information that is not only just coral cover, but also brings together spatial and environmental data layers to add context to the changes that we're seeing. Hopefully this works. I think I tested, yeah. This is a quick summary, a video of the public dashboard, that once you actually make your data sets publicly available, we can then summarize it into the public dashboard. This is Palau, and we can show you temporal trends of coral cover on the left, but also the changes that are happening on the right at the spatial scale. But we bring environmental data layers like NOAA degree heating weeks, data sets over time and space to actually add information and context about changes, but also cyclone models that we have developed at AIMS to add more information about changes in cyclone damage that could happen in a particular country or region of a country. But perhaps you might not be necessarily interested on a country-level summary, and you might be more interested, if I'm a manager of the state of coral in Palau, I can now then click in there and summarize the results for that, for the state of coral. Or I might be more interested on a particular site, so you can dive even deeper at that particular site and see the effect of those disturbances that had happened and trying to kind of use that information to explain why they're happening. So part of this work has been evolving very quickly, and now we recently released some additional resources. It's still work in progress, but we'd love your feedback on that. This is, if you go to the reefcloud.ai, you can access the whole portal, but there's the Get Started section where you can get access to a suite of resources, including videos and documentation, but it's a set of like data analysis vignettes in R that you can also explore. Before we finish, I just want to leave you with these figures, because what it means is that for this context, for this conference, we really are moving very fast in terms of like bringing information together and catalyzing actions. And it's been amazing, the uptake of Reef Cloud. We now have users across 87 countries around the world. It's been increasingly uptaken by the community across the world. But it's a big challenge now that we need to actually move even faster to help the community deliver a lot faster results that are a little bit more complex. So if you are interested in talking about that, I'd love to discuss it. But with that, I'll just want to leave you with thank you and happy to answer any questions.
Thank you, Manuel. Do we have questions?
Thank you, that was really interesting. You showed really good matching between Reef Cloud and the AIMS LTMP. What sort of frequency of photographs does that require to match the good estimation?
Yes, it's a very good question. We have found, but it changes a lot, but we have found that generally between 10 and 30% of the images that you use for training the algorithms produce a really good result similar to what we've shown there. Now, it depends on the complexity of the data sets. And in the case of the AIMS data sets, we're privileged because 30 years of data has been manually annotated. So we can do all possible combinations of iterations in that sense. But generally speaking, we found that if you have a relatively short label set, like say 50 labels, and then you have like a good consistency between your users and your annotators, you tend to actually get very decent results with only 1% differences between you and the machine, with about 20% of your data sets being manually annotated. But don't quote me on that.
All right, well, thank you, Manuel.
Thank you.
Great talk. Round of applause, please. Okay, so we do have one more talk. Actually, I'll go up onto the... So we have another video. Oh, we have another video presentation. It's from Sophie Gordon, and we will have questions after it.
Hi there, my name is Sophie. Thank you for the great presentations in the symposium so far, and I apologise I can't be there in person to present today. First up, I'd like to acknowledge the large number of co-authors and contributors that are involved in the large body of work I'll be presenting today. I want to thank them all for the opportunity to share this work with you. I'd like to share my appreciation as well for the contribution of and emphasis on traditional owners in this conference. I want to acknowledge that sovereignty was never ceded and that all research presented was conducted on sea country with full, free, prior informed consent. So there's been quite a few other presentations in the symposium so far referencing photogrammetry and related image processing and AI tools. So I hope you're all warmed up, you've enjoyed the talks, and make sure you keep a lookout for the recordings if you missed any and you're interested. So in this talk specifically, I want to provide a brief overview of photogrammetry's application in quantifying key reef metrics for understanding reef resilience and informing restoration. So photogrammetry refers to the use of photography to map and measure objects in the environment. And while terrestrial photogrammetry has been used since the 1800s, underwater photogrammetry has only really increased in the last 10 years. All photogrammetry, however, consists of a few key aspects, namely a camera rig, reference markers to scale and georeference the models, and of course the collected photos and benthic imagery. These images go together to create 3D reconstructions of the environment of interest or a digital twin. And when we talk about coral reefs in 4D, we're not exactly time traveling, but we are talking about time series 3D reef data. So the process of photogrammetry involves first divers or vessels collecting imagery continuously in a systematic pattern across the area of interest. These photos are then fed into a photogrammetry software such as AgiSoft Metashape, which uses structure from motion algorithms to build models. These models are constructed by first locating clusters of pixels from multiple photos and triangulating their position in 3D space to build what we call a point cloud. Triangles are then interpolated between these points to build a solid surface or mesh, forming the 3D model. Next, the photos are wrapped across the mesh to create a textured model as shown here. If we're assessing the change or comparing models through time, models from 2 time points are then lined up in 3D space through a process called co-registration. This is done before the final outputs, 3D models on 2D photo collages called orthomosaics can be exported. These outputs are then analysed using a range of methods to extract a diverse array of information. So this is an example of 2 3D models that are captured at different spatial scales and could be used for different purposes. For example, large area models like the one on the left can be used to assess habitat characteristics, whereas on the right, colony scale models can be used for more fine scale growth measurements. Similarly, depending on the purpose, 2D photogrammetry products can be used to examine large spatial trends using imaging techniques such as vessel-mounted imaging rigs, or close-range spatial ecology could be examined using diver rigs. So photogrammetry can be used to assess many ecological metrics related to reef resilience, recovery and function. For example, in this diagram by Orzo, we can see spatial, demographic and environmental factors that all influence recovery of reefs. So nearly all of them can be directly measured using photogrammetry. Furthermore, if you saw Manu's talk yesterday about vital indicators of reef health, we can see that most reef metrics that require monitoring can also be quantified using photogrammetry. This can dramatically increase in-field data efficiency relative to using different methods to measure each metric individually. So the methods by which these different data are extracted from 2D and 3D photogrammetry outputs are varied and use a wide range of different software and platforms. The techniques that this data can be extracted using can range from using AI-integrated classifiers to detect, segment, and identify coral taxa, such as in a platform like TagLab. You could examine spatial clustering and distribution of taxa from 2D models in ArcGIS. We could extract 3D habitat complexity metrics, such as rugosity, from 3D models using Python codes. Or we could measure 3D or 2D growth of coral colonies using these or other platforms. We can also compare all of these data across time to inform temporal patterns and trajectories. So as part of the EcoRAP sub-program of RAP, we've been designing, testing and applying a time series photogrammetry pipeline to examine many of the factors influencing reef recovery and resilience in order to better inform on the what, where, why and how of reef restoration. So this project spans over 350 sites on 17 reefs in clusters spanning the Torres Strait to the southern Great Barrier Reef, at inshore and offshore sites, and in different reef habitats and depths. So this project has also been running for 4 years. So each zone shown here is approximately 1,000 square meters in size and is imaged using high resolution DSLR techniques in each of the plots shown and GoPro techniques for the larger spatial extent. So the current outputs of this ongoing project include the production of a series of manuals and standard operating procedures describing the techniques used. These are designed to enable other users to replicate or adapt these techniques for ecological monitoring and research. The first of these manuals relates to data collection techniques and is available on the AIMS website or through this QR code, while the other two relating to model processing and data extraction are due to be published in the upcoming months. In addition to these manuals, Python scripts and AI classifiers will be made open source and available to all users for their own applications as well. All data and metadata created in this project is available on request and can be accessed through the AIMS data portal. And we've also uploaded a low-quality version of all of our 3D models to view and download on Sketchfab. So please contact myself or Renata if you're interested in collaborating or accessing any of these data sets. We're also planning to publish some data papers to make these sets more available and accessible to a wide range of users. So now the fun really begins. We have been collecting data for 4 years, and now our team is currently up to their necks in analysing and writing up all the data. So if you caught Renata's talk yesterday, you might have seen a sneak peek at some of the first large-scale pattern analyses of benthic community composition and distribution across the Torres Strait and Great Barrier Reef. Watch this space for upcoming publications regarding a range of spatiotemporal trends in reef metrics across the Torres Strait and GBR, and an examination of how they relate to other essential functions influencing reef health, resilience, and recovery. Now, if these aims weren't ambitious enough, I'd also like to share a few examples of some of the other projects and photogrammetry applications that our team and collaborators have been working on to give you a bit of an idea about some other examples of how these diverse tools can be applied. So I'm sure you're all aware of the recent declaration of a mass global bleaching event that's currently unfolding on our reefs. So while photography is a fundamental tool for assessing bleaching, we've currently been developing tools to apply photogrammetry to facilitate assessments of bleaching at larger spatial scales and over larger colony numbers. So an example of this is Mariana's presentation on Tuesday, which showed how the use of photogrammetry in the 2022 Central Mass Bleaching event could enable the extraction of large volumes of data relating to taxa identification, bleaching severity and extent, multiple colony size measurements across large spatial scales with minimum in-water input. Furthermore, the use of photogrammetry enabled the analyses to be adaptive to trends observed. For example, this allowed us to collect data on taxa that were not anticipated to be assessed, but displayed unexpected responses. So over the last few weeks, our team has also been out conducting photogrammetry surveys of over 24,000 square metres of reef across the Torres Strait and Great Barrier Reef. So in conjunction with this, we imaged over 2,000 colonies and assessed them for bleaching severity and in-water extent, with the intent of training an AI model to automatically quantify bleaching from the imagery. So using time series photogrammetry techniques, it also allows us to provide powerful tools for communication and sharing information about the impacts of disturbance events with others. So here you can see two slider comparisons of inshore reefs in the Central Palm Island group and the Southern Keppel group prior to and after the recent bleaching event. QR codes for these interactive sliders are available here, as well as a conversation topic in which they were published yesterday. So photogrammetry techniques are also being integrated with AI and automation technologies at an increasing rate. This includes developing autonomous vessels and processing pipelines to automate image collection and model creation over large spatial scales, as well as the incorporation of new AI image segmentation and classification tools to automate the extraction of data from 100% of images captured to increase the available information by orders of magnitude relative to traditional point subsampling methods. So in summary, I hope I've helped increase your understanding of the many ways that photogrammetry can be used as a tool to assess key reef metrics to inform on reef resilience and restoration, and maybe even will spark some ideas about novel research questions or applications in your area of interest. So I'd like to thank you all for your time, and I'd like to acknowledge again the huge amount of work and the large number of people who've contributed to this project and the work we do. Please feel free to contact myself or Renata if you'd like to collaborate or access any of these data sets mentioned, or to chat about how you might want to apply these technologies to achieve your goals. Thank you and enjoy the last day of your conference, and thank you to Renata for fielding any of your questions.
Hi everyone, I'm Maureen, and I'm part of that EcoRap team, so feel free to ask me any question and I'll try my best to answer.
I do have a question. So they were talking about scaling up and using those robotics and kind of trying to create an automated system. How far away is that?
I have no idea.
Okay.
It's
wonderful data and it's fantastic,
Yeah,
and it would
yeah.
great to be able to have that at scale. But it's a lot of work, and I know how much work it is as someone who works in similar areas. To be able to scale that up is going to be an amazing effort.
Yeah, it's more the work of Reef Scan and Scott Bainbridge, so he would be the best person to contact. And yeah, they're really scaling up and so building these orthomosaics, but for even bigger scale, so yeah.
Awesome.
Hi. Do you happen to know what the size of each of those models are, and maybe talk a little bit about your data storage plans and how much space that takes over time?
Petabytes. So yeah, we're fortunate enough to have AIM servers to store all of our data and multiple backups. And so the size of each model is 12 by 6 meters, and the size of the outputs depends on what the output is. So obviously the 3D model are quite heavy. So yeah, that's something that for sure needs to be accounted for before collecting all these data, because yeah, you have the raw images and then the different outputs at the different steps.
Well, it's wonderful, innovative research. Thank you, Maria, for answering those.
Thank you.
And I guess we'll move on to the next talk. Round of applause for Maria for helping too. For answering those questions. Tough. Okay. Oh, it's Joel. Welcome to the stage, Joel Alro. He'll be speaking. Well, I'll let him introduce what he's going to be talking about.
Thank you very much. So I'm Joel Alro from Queensland University of Technology, and I'm working within the RAP program, the cooling and shading sub-program. So a lot of what I've been going to be discussing has already been introduced by Dan in his keynote earlier today, but just in case you missed it, I'll go through a few of the details, and looking specifically at our fogging initiative to solar radiation management initiative. So Dan talked about, we've got really two initiatives we're looking at. One is the cloud brightening program, where we're trying to change the amount of radiation getting through by modifying cloud brightness. This is a related concept, but subtly different, this fogging process, and we're specifically targeting doldrums-like conditions. So just to recap, in case you forget, that's when we have negligible cloud cover, we've got very low wind speeds. As a result, we've got quite reduced ocean currents and typically much less turbid water, so you get much greater penetration of sunlight through to the coral. So what we have is already highly stressed corals due to the heat in the water, and then they're getting this overload of solar radiation, and that can often be the trigger point that kicks off bleaching. It's a real threatening time for them, and so what we're not trying to do with the fogging is cool the water. This is actually just trying to reduce that amount of sunlight getting through to the coral themselves and avoid that conversion into bleaching. So there's already been some studies that have looked at how shading can be used, can be deployed over reefs to improve their mortality, usually with some kind of physical measure like shade cloths or structures like that. Typically it's not particularly easy to scale over something particularly as large as the Great Barrier Reef. So that's why we're motivated to look at instead using a fogging type technique. But still, we're interested in quite a targeted, this is a targeted initiative here. So unlike the marine cloud brightening, where we're trying to affect massive areas of the Great Barrier Reef, have a wide-scale sort of influence, this is looking specifically at high-value reefs, either high-value or highly vulnerable reefs. And I think it's particularly exciting because today I'm hearing about all of these other initiatives that people are working on, the nurseries that are being developed, and the restoration of damaged reefs. And so this is a way that we can provide localised, targeted protection for those sorts of areas. So yes, it's a targeted intervention at the scale of individual reefs. It's intended to be rapidly deployable. So you become aware that there's going to be these doldrums-like conditions. They're going to be highly dangerous for the coral, and you race out there and provide this targeted shading just for that period of doldrums-like conditions to try and get them through, give them that breathing room. It's using natural seawater, so we're pumping up seawater, spraying it out, and creating a persistent fog that spreads out over the region. As Dan mentioned, the great thing about the seawater is, unlike fresh water, it does actually persist for quite a long period of time instead of just evaporating away. So just going to talk you through the process we've gone through in terms of developing this technique and some of the history and where we're at now, where we're moving forward to. In terms of the development, really there's some key parameters that we're focusing on to get some really good shading. So we need to have really high droplet production rates and so that we have nice dense plumes and covering as large an area as possible. But we have to bear in mind that all of that water that we're pumping up requires a lot of power to draw. And so we have a bit of a trade-off there. We want as many droplets as possible, but they also need to be as large as possible so that they effectively interact with the light and you get really good scattering. So we've looked at different wavelengths of light, where they receive the most scattering effect, interact most with these droplets. And if we balance these two requirements together, it turns out that a target diameter of around about 400 to 500 nanometres is probably the best point to aim for. So following on from that, we've done a bit of due diligence just to make sure that we can actually achieve some tangible, sufficient shading using this method. So we've done some fairly traditional, somewhat simplistic sort of mathematical modelling, some simulations, treating the plume as Gaussian sort of plume, meaning that it has this very uniform kind of shape over time. If you average it out over time, that it's spreading out from a central line, and that we were finding that looking at different weather conditions, really, really low winds or the higher ends that you might expect for doldrums-like conditions. And for the best conditions, we found that we should be able to get somewhere between 15 to 30% shading over an area of 2 to 3 square kilometres. So that's certainly large enough to cover your standard sort of coral atoll. For higher wind speeds, that starts to decrease, of course, but still we should be able to get something in the order of 10 to 20% shading out to a distance of at least 1.75 kilometres if this modelling is correct. So it seems to be worth going ahead with, and we went ahead and came up with a prototype or proof of concept, bearing in mind what we're trying to do here is get this out as quickly as possible, because as we've seen, we had the great keynote earlier today. Sorry, I forget the presenter's name from a University of Miami, just talking about how we are in such a crisis point right now. We don't have time really to wait around here. We need to be coming up with our solutions as quickly as possible, and so we're taking off-the-shelf components rather than spending a lot of time to develop new technologies. And so we're deploying these MeFog impact pin nozzles that just have their little orifice that we pump the water through, and that hits a little pin and creates the spray, pumping this water at really quite high pressures. we started off with mounting these around a Osmist fog generator, just a turbine, 100 nozzles around that, and deployed it at a couple of land-based sites just to demonstrate that it worked effectively. And what we see here is quite a substantial plume, measured 50 metres away from the generator, getting a nice sort of dense plume there, and we actually saw it extending several paddocks further away. So everything looked good there and gave us the justification to scale up further. So now this is our most recent prototype that we've come up with. It's we've got 4 rectangular modular arrays, so 10 times as many nozzles, 1,080 nozzles in total, with their own pumping, water pumps and filtration units. And you can see here, much more dense plume that we're getting. So really now moving up towards the scale of what we need for the Great Barrier Reef. And you can see here that we were able to, we've been able to get it out onto the Great Barrier Reef now. So in March of 2023, we went out to One Tree Island Reef, so that's near Heron Island, and we're able to deploy it here and take a whole suite of measurements there, mostly with surface level vessels moving back and forth underneath the plume. So primarily relying on these transects moving back and forth around about 400 metres behind the source, and also within the lagoon further away at about 1 to 1.2 kilometres away. Constrained somewhat to those locations just because of all the reef structure around there. But that gave us the opportunity to really evaluate what we were producing. So just quickly running through some of the results we've had so far. In terms of the size of the droplets that we're producing, we're able to, what we see here, the first graph on the left, that's looking effectively at the number of particles that we're seeing at different diameters. And the key point is, I'll mention that the scale there on the x-axis is given in measuring the dry particles. So if you dried out all of the water, that's how large they'd be. In the marine atmosphere, you can basically double those sizes. So we can see that the majority of the particles are in the order of 400 nanometres or higher. So it's fairly close to our target. Not quite there. We've got a little bit of room where we'd like to hopefully change up our spraying mechanisms and hopefully push those sizes somewhat larger. But we also saw that it is significantly dependent on the humidity. So if you have a particularly humid day, those droplets will grow to larger sizes and you should get more effect. We also saw the shading, in terms of the shading at those 2 points that we were measuring. We saw between 12 and 20% shading and 13% shading out at the further distance away. So that's in line with the slightly stronger wind speeds that we were modelling. But we did see at least one point significantly higher shading, certainly not representative of the longer time period or the whole area that we're shading. But we feel like this shows that we've got some room to play with if we have really good conditions, and if we can improve our processes, we're definitely in the right ballpark here. We also saw that we've basically got a little above 10 hectares of coverage based on the range that we were measuring, and we certainly saw it expand further beyond that. So again, we're getting some good coverage, and we're hoping we'll, once we can fully measure the scope of the plume, we'll be on target there. That sort of highlights a bit of an issue here. It would be nice if we could be really concrete about exactly what we're producing now. We would love that as well. And I just want to use that as a chance to mention some of the challenges that we face with our field measurements, and use that as a context for where we're moving forwards. So when we're out there trying to take these measurements of the plumes, first and foremost, a big trick here is that doldrums conditions, super important. Like, these are these times where the coral are at so much risk and can be that trigger point for bleaching, but they only happen in a handful of times per month of the bleaching periods, or the summer months. So you have to be Johnny on the spot to catch those days. And of course, it's a lot of infrastructure and time to get out there with all of the ships and the staffing and all of the equipment, a lot of expense. to hopefully capture enough data there. So that's a limitation, and we just need more time to get more data effectively. We need really sophisticated instruments to get accurate measurements, but that therefore requires fairly large platforms to do our measurements on. And so it's hard to have really distributed measurements with small sensors mapping out the whole plume. We have to rely on much more sort of localized measurements. And the plume itself doesn't really like to behave. It moves around with the wind, and you can see it has a very complex kind of structure, not like the simplistic sort of Gaussian profile we had in the modelling. All of this just complicates the measurements and ultimately means that we need to get a lot more field measurements to get a concrete picture. And so just to wrap up and tell you sort of where we're going with this, I think that motivates that we want to put more time into, currently in the progress of, developing a much more sophisticated large eddy simulation modelling where we get the real dynamics of the plume and are able to really represent the plume much more accurately. And if we can nail that, then we can apply that to all different kinds of weather conditions, different types of spraying conditions, changing up the way we do our production, and take our reliance off the field measurements and instead get our results from the modelling. Of course, we still need to do a lot of field measurements to confirm that the modelling is correct, so that won't go away, and hopefully we can do that during a bleaching season over an area where we have well quantified coral properties and see the effect on those coral. And we have some ideas about how we might be able to increase the spread of our plume by having a moving source or maybe splitting up our generator across smaller vessels. And ultimately coming up with some really effective strategies and protocols that we can use then to roll this out to full operational deployment. So it's exciting times ahead. Thank you.
Well done, Joel. Really interesting stuff. Do we have questions for Joel? I know it's getting late, but you know, we've got to keep the energy up. Manuel.
Thanks. Also presentation. Thanks a lot, mate. Just had a question about like the next steps. So you're talking about increasing coverage and sort of efficiency, and I know this is a big challenge. I just want to know, are you looking into also increasing the shading? Because like we have found from some experiments on the water that we need a little bit more than what you're getting. So like we need about like 30%, 40% shading. Have you looked into it? Sorry, I don't want to criticize your work, but I think you're doing an awesome thing.
Yeah, no, you're absolutely right. Like these are the main things. We want to make sure we've got enough coverage. We want to make sure that coverage is dense enough that we are reducing enough light. You're absolutely correct. And yes, absolutely, we want to get as much as we can. I think part of that will be if we can push these droplet sizes a little bit larger, then that will have a big effect on the amount of shading we're getting. I think also part of it is that we somewhat limited by, as I was saying, with the data that we've got now, really understanding how the longer-term average shading that we're getting in the region. So I think there's a lot of space to improve our quantification of how much shading we're getting. But yeah, I think it's going to come down to if we can improve our the engineering of the nozzles and the production methods to get a denser plume. Yeah, thank you.
So a round of applause for Joel, please. Okay, so there's a bit of a situation here. I am chairing for myself. So Mia hasn't showed up. She was going to do this, but I will introduce myself instead. So the next talk is for Brett Lewis. Please give him a round of applause. Okay, so let's keep that energy up. It's the last talk of the day. I promise I won't take too long and bore you all as much as, well, actually I don't promise. My name is Brett Lewis. I'm from Queensland University of Technology, and I'd like to welcome you here to this talk. I'm going to speak about novel bioadhesives for rubble stabilization. So what is a rubble reef? Well, it's definitely not that. This is a rubble reef. Why is it a concern? Well, what happens is when we get an increase in rubble, we often get a decrease in three-dimensional complexity of these reefs. That means the reef becomes a little bit flatter, a little less complex. What happens then is we get a water diffusion, or less water diffusion, a decrease in water diffusion. This ultimately will increase water velocities. When water velocities increase, we often keep this rubble in motion, and that's when the rubble becomes a bit of a problem, is when it is mobile. Once it's mobile, there's less available substrate for natural recruitment, but there's also less available substrate for us in restoration. So these rubble patches become a bit of a concern, particularly globally, as RAP tries to scale up. Our mission now is to save Earth's reefs. We need to take into consideration rubble patches because they are a huge problem throughout the Caribbean and are a growing problem throughout Indonesia and other Pacific islands. So how do we stabilize rubble? Well, we're going to have a bit of a look at how it naturally stabilizes first. There is a two-step process, which the first one is preliminary stabilization. So this was from a publication by CSIRO in 2020. This preliminary stabilization is the initial steps. This requires interlocking of the rubble branches. It then requires pioneer binders, which are algae coming over the top. And then there will be intermediate binders, so sponges, ascidians, softer binders that will come in and form a matrix around this rubble and start that stabilization process. So then CCAs, calcium, carbonate building biomineralizers, microbialites, I should say, and corals can come in and start cementing that framework together. But of course, as you could imagine, as those hydrodynamics increase, as three-dimensional complexity decreases, and these cycles of constant destruction of reefs continue, these processes are going to stop happening. However, the good thing is they give us a bit of a roadmap as to how we could stabilize reefs and do it pretty effectively. So recent research into these areas by Tanya Kenyon and her team have started to have a look at how strongly this rubble is required, like what kind of binds are required in and around this rubble area. And they found that the forces that these binds usually consist of are around 12 newtons. So this gives us a bit of a framework, what forces we need to achieve with a bioadhesive in order to potentially, create a framework ourselves. At the same time, what are the velocities that these are resisting? So ambient velocities that these resist are about 0.2 to 0.8 meters per second. So again, we're starting to produce a framework for how the bioadhesive might work. But before I move on to any results, I just will talk to you about the bioadhesive because I'm sure not everyone is an adhesive expert. So number one, cohesion. Number two, adhesion. They're the two things you need to know the most. Whenever it comes to, even if you're going down to Bunnings, they're the two things you need to know. Cement has great cohesion, which means it's hard. It holds together. It holds its structure. Gum has terrible cohesion. It gets pulled apart very easily, right? But gum has great stick. It'll get in your hair and you'll never get it out. Cement, it takes a little while. You'll be able to wash that out as long as it's wet still. So it has bad adhesion. Now, these are two factors that we look at. However, there are other things like durability, which is the other two factors over time, and it's this tunability. Now, this is the reason in the first place that RAP started looking at bioadhesives, is because of this tunability. What that means is we can take any chemical component and start adding it to the bioadhesive to basically change how it behaves, right? And this allows us to create a bioadhesive that is fit for purpose. Of course, just developing a bioadhesive takes quite a bit of time, and then testing it also takes quite a bit of time. So we can start to add things like starch, cellulose, other plant wastes into this material, cheap products, and we can start changing those factors. But since I've come on board, we wanted to expand that a little bit more. We want to create a suite of adhesives for rubble stabilization. That means looking at other different things like magnetism, the viscosity of the material, the biodegradability, and of course getting that cost as cheap as possible. And just to give you an idea what cheap means in the bioadhesive world, QUT just sold a bioadhesive for $80,000 per 100 grams. That's what it gets sold at the moment at market value. Ours should be around the $2.50 below mark for 100 grams at the moment, but we should be able to get that lower as we continue to talk to companies. So other things you need to know is that it's plant-based, it's 75% biodegradable, 25% degradable. It uses a cross-linking attachment mechanism rather than mechanical, which most adhesives use. Cross-linking is a chemical process, so it chemically bonds to the surface. And it's made from common plant waste material available globally, anywhere. So it makes it easy for us, not just here on the Great Barrier Reef where we have a lot of resources, but also in other countries where they may have less resources, but as long as they've got palm oil or cane farms, they're going to be able to build this bioadhesive. So for the last 12 months, I've come on board to basically take this base bioadhesive that was built over the first 3 to 4 years of RRAP and test it and refine it and test it and refine it and produce this suite of bioadhesives for a rubble stabilization here, but hopefully broader applications as well. But I will only talk about rubble stabilization. So the first thing we want to look at is compatibility. Is it going to be okay for the reef? And you can see here the blue line at the top is the red line at the top. You can see here is what happens when you put the bioadhesive in 200 mils of water. You get a deoxygenation event. Obviously, corals and a lot of marine organisms don't like this, right? So we wanted to see whether or not that's going to scale. So even just putting it in 500 mils of water and running the same trials again, we saw the deoxygenation event shifted more towards the control. And basically, as we scale to ocean levels, I really don't see that being a huge problem. And we did find that whenever we place anything next to the bioadhesive, they all survived. But of course, we want to continue to test these things. So we had a look at some clean substrate tiles and placed the bioadhesive on that to see what colonized around it in the aquariums at the sea simulator. And we can see here that there actually was a bit of a shift. So compared to the controls, we had an increase in CCA and a decrease in fleshy corals like lobos. So there was a bit of a shift, and it was significant as well. However, that didn't show on the actual rubble pieces. So when we tested this bioadhesive on the rubble, we saw no population shift at all. That's likely because there was already a fairly well-established community, and it was probably difficult for the bioadhesive to get involved in that. But at least it didn't shift the community, and we did actually have some spats start growing in and around the bioadhesive on those rubble pieces. That brings us to the bad result. So when we tried to settle algae around it, and you could imagine what it would be like to do this in 10 mil of water, there was a heavy deoxygenation event, and it killed the spats in 10 mil of water. I'm sure at scale it's probably not going to be a big problem, and you can see with the spats in the previous image, it doesn't seem to be. However, we did take this result and we wanted to have a bit of a look, and we started tuning a new adhesive using an alginate. And it settled 50% of spats once we were done with that. And all larvae were alive, all planula were alive at the end of the trial. So that was over 24 hours. Both trials were. So compatibility-wise, it looks pretty good, especially for rubble stabilization. We also want to have a look at the strength. So we did 2 tests, one on rubble and one is a standardized process. So at the bottom there, you can see that's the standard. So it's just a little plug-on-plug action. It's just giving us a flat surface, something that we can replicate. And then the top one is obviously rubble. It's going to be a lot more inconsistent. It's rounded, irregular texture, and so on. And plus, it also has a biofilm, which is painful to try and deal with. But what we found was the T2 on the right, so to give you a bit of context, the T2 is the first bioadhesive that we produced, and it's the T2 is the bioadhesive I was given at the beginning of this project. And these are the new ones that we've developed since then, the R1 and AG5, and they're producing much better forces. And when we compare that to what the forces of binding are in a natural reef at that early preliminary stage at 8 to 12 newtons. These are significantly going beyond that. And just to give you an idea, KPA is just newtons adjusted for surface area, so it's a relative number. It's actually a conservative number. The newtons are actually significantly higher than this. So that pulls those numbers down. So we're absolutely outstripping natural binding. And you can see it there. Again, that's on the rubble pieces themselves, so not on the standards, that's the rubble and the difference between them. So then, of course, we want to go to translation, we want to start scaling up, we want to start testing things. Next, we wanted to look at, oh, the video's not playing, okay. But that top one there is a flume system. Oh yeah, there you go. The top one there is a flume wave system where we tested the bioadhesive in that, and over all 24 sets of experiments that we did, we never had one piece of rubble move or detach during that at 0.5 meters per second. Now, it's only at 0.5 meters per second. They're ambient conditions on the reef. Obviously, you're going to get worse. But just to be clear, we're also never going to stick down one piece of rubble at a time. That's never going to be the goal. It's going to be creating a mass. So we really want to see how the mass will interact eventually. But we also wanted to test this at higher flow rates. So we got them to resist at 20 mils, only 20 mils of adhesive, a very small amount of adhesive was able to resist 1.4 meters per second. So that's about 3 knots. So that's pretty good. But of course, we'll hopefully continue to refine and make that even better. Other things that we're looking at now is we're testing different methods for outplanting. Austin, even though he's not in the room, had a great idea of this nucleic kind of centralizing coral reef restoration, similar to what they do with deforestation or reforestation. And we want to do a similar thing, create nucleuses of stabilized patches and then hands-off allow the natural processes to then take over. So long as there is a stable area for the rubble to bind and interlock to, it should do it itself. And the good thing is, if it fails, if we fail, if this doesn't work and we do put a bunch of this stuff out on the reef, in 5 years it won't be there, which is not what we can say about a lot of our interventions. Obviously, it would be the goal to be like that, but this one, hopefully, we won't leave any footprint behind regardless, other than a good footprint, hopefully. But thank you for listening to my talk. Oh yeah, and hopefully in 2025 we'll scale up to those that reef scale application. I have to keep my own time, so I need to move myself along. So thank you. I'd like to thank everyone that's on this screen and everyone in this room for sticking through the conference and coming to my talk at the end of the day. I think that's lovely, and you're all my favourite people. Thank you. Do you have any questions for me? I just realised I'm still chair. Thanks, Kevin.
No, thank you, microphone guy. Thank you, microphone. There we go. Thank you, Brett. Yeah. Brett, I'm going to need thousands, tens of thousands of kilograms of this bioadhesive. I'm scaling everyone. I need that. How can I have that much, and who's going to make it for you? And is that available in this state or in this continent?
So you'll have to speak to Aric Bickel. He is my only person that I have making the adhesive at the moment, and he's not even full-time. So at the moment we're trying to start discussions with Henkel and SECORE, both two of the world's largest adhesive producers and manufacturers. And there are some potential other avenues, but we really do need a lot of this stuff. And I don't know yet how that's going to look. Hopefully they can also make it cheaper because they'll have supply lines that we don't. Thanks, Kevin.
Brett.
Anybody else? That's the last talk.
Thank you. I'm just wondering what the basic setup times is for this glue.
So for like rubble application or just to make it in?
Yeah, for gluing applications.
So for gluing applications, to make the bioadhesive, it's actually really quick. It takes as long as you have the materials there. I've seen them, and it's only small amounts that they're making for me, but they can make it in like 2 or 3 minutes. It's all mixed together. Obviously, when you're scaling, and it'll probably take a little bit longer, so I wouldn't use that as an accurate timeline. But to apply it underwater and to deploy it, and that's something that I'd really have to work out logistically. I really don't have an answer for it. I hope that everything will work perfectly and we'll be able to deploy this rapidly. But for now, we'll just have to get some divers down there with some buckets and see how it goes.
But what's the actual, like once you apply it, what's the setting times on it?
Oh, setting time. Oh, okay. So sorry, with the bioadhesive, it doesn't have a setting time.
Oh, right.
So cements and things like that, they often have a curing time. The bioadhesive won't cure. It will adapt to its environment. So I actually meant to bring a sample. It's in my bag. Is it in that bag? Yeah. And so it'll be hard, right, to start off with. In the air, you can have it hard, but if you place it underwater, it will soften again. Or if you place it underwater, it'll start to harden to a certain degree, but it'll never get completely hard. And that threshold as to where it reaches its maximum, we're still kind of working on, but after we see after 15 days, it's still getting stronger.
Yeah, okay.
So we haven't quite hit that mark. I'm testing over 30 and 60 days now. So the first set of trials were just for 15 days over 10 adhesives, and now we're testing, refine those adhesives, picked a couple, and now we're going to test it for longer to see if it continues to get stronger over time.
Okay, thanks.
Thank you, Brett. And everyone can head off to the plenary. Straight to the plenary, everyone.